Hey guys, just let me know if you guys can hear me, please. All right, great. Okay, so some of you all would have attended my free CSEC chemistry session. You guys got a really nice paper there for chemistry. So when it comes to physics, we're gonna have the paper 2 tomorrow, and hopefully we get a nice exam, right? Hopefully we do get a nice exam. Um, so I'm gonna see how much time I can give you guys here. So we're gonna do some past papers, but before I even reach there, I want you all to understand when it comes to your exam, there are basically a few things that you need to focus on. When it comes to your definitions, you all need to know your definitions very clearly and precisely, right? So all your definitions, you need to know them. So if I were to ask you what is density, you should be able to tell me density is mass over volume. If I were to ask you what is meant by the amplitude of a wave, you should be able to tell me maximum displacement from your rest position. Typically, the paper is going to be six questions, right? The first question is a data analysis, which is 25 marks. You all should only spend half an hour working on that problem. If you find yourself going more than half an hour, then you need to move on. The remaining 5 questions are worth 15 marks each. And in terms of the structure of those questions, the first one, or the first part of the question, is generally some definition of sorts. And we may get some explanation. So you may have to explain something in the question. And the majority of the question is going to be based on calculations using some formula. So you know, if we get a question on density, if they ask you for the definition for density, then chances are they might give you some scenario where you might have to explain something, and then we're obviously going to have some calculation. Now, when it comes to calculations, we need to be very clear in terms of what units we are using, right? Based on what units we're using, right? Okay, so let's see. Right, so I'm going to focus my attention on exam papers because I don't know if you all know this, but CXC repeats questions in the paper 2 as well, not just the paper 1, right? Okay, so I'm going to run through this paper here. This is May 2019, okay? All right, so this question here is based on transformers. We have figure 1 is a diagram of a transformer, and we need to label the parts X, Y, and Z, okay? Now, they've brought this question several times over the years. So X here is your AC input to your transformer. A transformer only works on alternating current. So X here is going to be your AC input, right? That's what X is. When it comes to Y, Y is basically your secondary coil. So this here is your secondary coil, right? And Z is your soft iron core, right? So Z is a soft iron core. Now, when you are given a transformer, you all need to understand how a transformer actually works. So a transformer operates under the principle of electromagnetic induction. That's how a transformer works. Now, when it comes to electromagnetic induction, basically, if you have a conductor that is caught in a magnetic field, an EMF is going to be induced in the conductor. So if I had a piece of wire, right, or a metal rod, and it's moving through a magnetic field, I can actually get a voltage across the ends of the conductor. So this is what electromagnetic induction is. If a conductor cuts a magnetic field, an EMF is induced in the conductor. Now, there are 2 ways we can make this work. You can either have the conductor moving in a stationary magnetic field, or you can have the conductor stationary and the magnetic field is moving. With respect to a transformer, that is exactly what's happening here. Your 2 coils, your primary and your secondary coils, they are not physically connected, right? They're not physically connected. But if we have an alternating current flowing in the primary coil, so by the way, you all have to be able to explain, right? You have to be able to explain how the transformer works. So this is how it works. Alternating current in the primary coil creates an alternating magnetic field. This magnetic field is located in close proximity to the secondary coil. So because the secondary coil is in a changing magnetic field, an EMF is induced in the secondary coil. So these are questions they can ask you regarding a transformer. The other thing they can ask you regarding a transformer, how does a transformer, or how do we design a transformer for maximum efficiency? So first of all, the transformer has a soft iron core. That is one feature of the transformer that makes it efficient. You see, the soft iron core, right, concentrates the magnetic field. It allows the magnetic field to change easily within the core, right? That's one. The core of the transformer is laminated. So instead of having a single block of copper, what happens is that they take that block and they cut it into slices. They varnish all the slices and then they stick it back together. That's what we mean by laminating the core of a transformer. That reduces something called eddy currents in the transformer. It doesn't eliminate it, but it reduces, right? The next thing that we can be asked here is with respect to the wires. So if you want to reduce the energy losses in the copper wires, you make the copper wires thicker. So if you make them thicker, right, that also reduces the power loss in the transformer. Okay, so these are things you have to be able to explain when it comes to transform. Now, what else we have in this question here? All right, so this is a nice data analysis question here based on transformers. All right, so this is what I have here. Now, guys, you will get a data analysis, and the data analysis could either be a straight line or it could be a curve. Now, we have a transformer here in figure 1 as this transformer, and we have the values for the primary voltage and the secondary voltage obtained. The data is shown in the table below. So we have primary voltage and we have secondary voltage. Now, let me just check the rest of the question here. All right, they didn't ask you to draw the circuit, but some of you all are doing physics as a private candidate, right? Some of you all doing this as a private candidate, and I want you all to make sure you understand how to get a table from, or a table like this. So basically, you're going to have your transformer here, right? And this here is the electrical symbol for a transformer. So you have a primary coil, secondary coil. Now you want to measure the input voltage and the output voltage here. So first of all, we have our AC input here, right? You have your AC input here. So this is connected here, right? So that's on your primary, AC input on the primary. You have your secondary. Now on the secondary here, we're just going to put a resistor to indicate that we have a load on the secondary. Now if you want to design an experiment here in order to collect this data, right? So I'm going to make a slight adjustment to my diagram. Hold on. So first of all, we need to be able to adjust the voltage on the primary. So what you can do, right? You can actually just use a variable resistor here, right? A variable resistor here, right? So we are going to measure your input voltage here using a voltmeter. So you connect a voltmeter across here. We also connect a voltmeter across here as well. So those two voltmeters are going to give us the corresponding values for the primary voltage and the secondary voltage. Now you want to plot a graph of VS against VP. So first of all, CSEC will use the word against, or they might use the word versus. This first variable here is always going to be a Y, and the second variable is always going to be an X. So I've seen instances where students, they go and they draw the graph, but they draw the wrong graph. All right, so you have to be careful with this, right? So let's see if I can plot this graph here for you guys. So first of all, the graph paper that you're going to be given is going to be black and white. To me, that's a little problematic because you are trying to draw using pencil, right? So you have to kind of draw the graph a little dark in order for the examiners to be able to see it. So in this case here, let's try something. All right, so this is here. It's my graph. Now I'll explain to you guys how CXC actually marks your graph, so you know how to get your marks as best as you can. So first of all, let's make sure we have VS is Y. So this here is your Y and VP is your X. Okay. So before you do anything in the exam, make sure you can identify what this is first, which one is which. Firstly, you're going to get marks for selecting a scale. You're going to get marks for that. So we need to select a scale on the X-axis. We need to select a scale on the Y-axis. You are getting marks for this. So you're going to choose a scale that allows you to maximize your graph paper. So first of all, on the X-axis, you have primary voltage. So you're looking at the smallest value, which is 1.5, and the largest value is 8 here. So first of all, let's put in our axes. So hold on, need some stuff here. All right, so first of all, let's put in this axis here, right? And let's put this one here as well. Okay. So step one, right? We need to label. So first of all, this is your X-axis, which is VP. So you need to label and put a unit. You are getting marks for that. And don't stress because it's right here in the table, but you're getting marks for that for labeling the graph, right? On this axis here, well, I haven't selected the scalars yet. So let's see, one. Okay, on the X-axis, I can use 2 cm to represent 1 volt, right? 2 cm to represent 1 volt. So if we go 0, 1, 2, 3, 4, 5, 6, 7, and 8. So we're just making it here, okay? So that's on the X-axis. On the Y-axis, now you're starting off at 14 and you want to go up to 72. So maybe we can go 10, 20, 30, 40. Right? Yeah, we're going to get up to 72. So we don't need to go that far anyway, right? So let's remove this here. All right, so again, you get a mark for this, so make sure and label. So you're going to label this as VS, that's your secondary voltage, and it's measured in volts, okay? All right, so first of all, right, so you're getting marks for selecting your scale. In this case here, I'm using 2 cm to represent 10 volts, okay? So let me just highlight some things here. So a mark for this, typically for scale. We get a mark for labeling your axes correctly. We're also going to get a lot of marks just for plotting your points accurately. Now, when you're plotting your points, you have the option of either using a small x or a dot with a circle around it. So whichever one you are comfortable with. So the first one here, 1.5 against 14. So 1.5 against 14 is going to be here. So that is plotted. Next one is 3.0 against 26. 3.0 against 25. 26. The next one is 5 against 45. 5 against 45. That's here. Next one is 6 against 53. So 6 against 50, 51, 52, 53. Then 7.5 against 6.7. So 7.5, sorry, at 67. This is 65, 66, 67. And then the last one here is 8.0 against 72. This is 71, 72, right? Now, if you just look at it here, there's a general trend where it is increasing, right? It's basically increasing. So the next thing you have to do, you have to draw a line of best fit. So I get this from students all the time. So how do we draw the line of best fit? Now, whenever you are given raw data and you've plotted raw data, you need to draw a line of best fit so that you kind of balance the points around the line. That's what you need to do. So you are getting a mark for drawing a line of best fit. So you need to balance the points around the line. That's what you need to do. Okay, so in this case here, this could be a reasonable line of best fit. That could be a reasonable line of best fit. Students normally ask me, sir, are we getting marks for labeling? So labeling like this, graph of VS against VP. You are not getting a mark for that, right? You are not getting a mark for that. That's nowhere in the mark scheme. I've never seen that in the mark scheme. But if you are worried about it, you can write it if you want. That's not a problem, right? All right, so this is my graph here, right? Make sure, right, you are at a stage where you should have plotted or you should have drawn many graphs already, right? You should have, okay? Right, somebody's asking me a question. Does your line of best fit need to go from the origin? Now, it depends on the question. Not all graphs will pass through the origin. I want you to follow your data. Whatever data they give us, kind of stick to the data. If you know theoretically, it should pass through the origin. In this case here, when you think about it, if the input voltage to a transformer is 0, I expect the output voltage to be 0. So technically, the graph is supposed to pass through your origin, right? Technically, it should pass through here. Okay. Now, usually when they give us a straight line to draw, the next thing that they're going to ask us is to find the slope, right? So, could you all work out the slope for me? Look at my graph, and I would like for you all to work out the slope of my graph, right? Hold on. All right, I'm just going to put this here. Right? I want to show you something. Look at this graph here, and I want you all to calculate the slope for me. Right? Somebody's asking me what question one. So there are several options, popular things that they bring in number one. They could give you in number one Hooke's law. They can give you Ohm's law. They can give you this one that we're doing here right now. We can also get one on lenses, right? So they're standard type questions that they could bring in question one. Once you've done about 6-7 years, you should be okay. Pen for what? For the graph? Now, when it comes to plotting, I would suggest use a pencil, please. Right? If you go and you plot your graph in pen and you make a mistake, how are you fixing that? Seeing some nice questions coming through here. Do we use plotted or non-plotted points? Generally, we will use points on the straight line. If your plotted point is on a straight line, then you can use it, right? Because that straight line represents all of your data. So really and truly, we are supposed to work this out based on the points on the line, right? Right? Because any examiners we had said to use pen. All right, good luck with that though, right? Hope you don't make a mistake. All right. All right, I've seen some answers coming through for the gradient. Somebody's asking for the chem solutions. I might do it over the weekend. All right, might do it over the weekend. Right, I've seen 8.8, 8.7. Some people got 67. All right, so I've seen some answers here. So let me try to work it out. So first of all, when you have to find the slope, you're going to select 2 points on that straight line that you plotted. Now you're going to select 2 points such that the spacing between the 2 points is more than half the length of the line, right? That's what you're going to do. So my suggestion to you is when you're selecting points, try to choose points that you can actually read off from the graph. Don't choose any random points. Choose points that you are able to read off from the graph. So for example, I could probably choose this point here, this here, right? Let's call that A. And this is what I would normally do. I would label the point as A, and then I will label a second point. So maybe this one here. This is looking like, all right, around 6.5. Select points, guys, that you can actually read off. Don't waste time choosing points where it's difficult to read it off. You have to work smart in the exam. So what I'm going to do here, and by the way, you're getting a mark for this, so please do it in the exam. You need to construct, you need to show CXC that you are drawing, right? You need to show CXC that you are drawing a triangle, completing a right angle triangle here, okay? All right, so I'm just completing this here. All right, so this is my rectangle triangle here. Again, you guys are getting marks for this, right? So please, you need to complete a right angle triangle here. So first of all, what I will do, if I have to work this out, I'm going to write down what is A. So the coordinates of A, according to my diagram here, is 1 and 9. So this is 1 and this is 9. My B here, according to my graph, is 6.5 against 58. 6.5 against 58. That's what I have. 6.5 against 58. Okay, so what we're going to do here, we're going to label before you work out slope, and I suggest this to all my students. Make sure and label this. You're going to call this x1, y1. We're going to call this x2, y2. If you do this, then there's no reason why you shouldn't get this correct. Okay? Now, next thing we're going to do now, we're going to work out. So it's called S. They're calling it S here. So slope is simply y2 minus y1 all over x2 minus x1. That's how we calculate slope. So my y2 is 58. So it's 58 minus 9 divided by 6.5 minus 1. So when I work this out, right, wish I could have showed you the calculator here, but 58 minus 9 divided by 5.5, I'm getting about 8.9, right? 8.91. That's what I'm getting for my slope. So I saw some of you all got answers close to that. So great, right? Great. All right. Somebody's asking me, what do I use to stream? Yeah, I've been using OBS since day one, right? So that's what I use to stream. Okay, let me just tell you something here. So some people say they got 9 and all of that. So first of all, CXC is going to give a range of answers for the slope. Now let me just give you a little pointer here. In this question here, CXC is asking us for the slope. But whenever you all work out the slope, make sure that you put a unit if there is a unit. In this case here, I have plotted what you plotted, and this is important here. I have plotted VS in V, right? And I have plotted VP in V. Now, if you want to know the unit for your slope, right? So the slope will have a unit, right? We're going to take the unit on the y-axis, which is V, and the unit on the x-axis, you're going to divide both of them, and you're going to get 1. So basically, they are canceling each other. If, however, I had plotted a graph, and let's say we had a graph here with, let's say the unit was meters per second, and this here was second, and I had a straight line here, and I wanted to get the slope. The unit for the slope, in this case here, will be ms to the minus 1 over s, which is equal to ms to the minus 2. Okay? So just be aware that you do get a mark for putting a unit for the slope. So this particular graph here has no unit because the voltages cancel. If you all ever did a graph of sine I against sine R for refraction, that will also have no units as well. Okay, so that's my slope. See what else we want to work out here. All right, so everybody copy this paper. I'll have to read it for you here. Use the gradient. So first of all, let's write down what is my S. So my S was 8.91, right? 8.91. So use the gradient. So we have to use this in our calculation now. We want to calculate the number of turns in the secondary coil, given that the number of turns in the primary coil is 85. So first of all, this here is NP, and that's 85. Now your slope right, is 8.91. Now, first of all, what did you divide in order to get your slope? So remember, you plotted a graph of Vs against Vp. So this here is Vs against Vp. Now, when you all work out your slope of your line, you are essentially taking Vs and divide by Vp. So your ratio of Vs over Vp, that is equal to 8.91, right? That is what we know based on our graph here. Now, the question wants me to work out what is the number of turns in the secondary coil. So we want to work out NS. So first of all, there are two transformer equations you all need to know. So this one says that number of turns in the primary over number of turns in the secondary is equal to the voltage in the primary divided by the voltage in the secondary. That's one of our transformer equations. Now, if you want to work out, what you want to work out? NS, right? You want to work out NS. So if I want to work out NS, let's cross multiply. So NS by Vp is equal to NP by Vs. So therefore, number of turns in the secondary is equal to NP, number of turns in the primary, multiplied by Vs over Vp. Okay, so that's what the formula is telling us. Now, the number of turns in the primary is given by 85. And the thing is, we know what this is. That Vs on Vp is what you just worked out here. So that's multiplied by 8.91. So in this case here, it'll be 85 by 8.91. Now, because we are dealing with number of turns, we have to round this off to a whole number. Okay, so in this case here, I'll put 757 turns. Right? Let me just make sure this is correct. So NPVS over VP. Am I making sense to you all? Yeah, so I'm watching some of your answers, right? Round it off to the nearest whole number, right? Round it off to the nearest whole number. Don't yeah. Somebody's asking me if if I did this here, right? Okay. No, I didn't put my hand in making any chem paper. I just understand what CXC does sometimes. Okay. Yeah, obviously your answer is going to be a little different, right? Depending on your gradient. That's why. Yeah, Hooke's law, pendulum, all of those are possible things that can show up. Yeah. All right, let's see the second part, right? The second part. Okay, in this case here, right? In this case here, we want to work out the current in the secondary coil. So we want to work out IS, right? That's what you want to work out. IP, that's your primary current, you know that as 1.8 amps. So, when it comes to current, right? When it comes to current, right? Just give me one sec, right? Give me one sec. Yeah, sorry about that. Okay, so you want to work out the current in the secondary. So first of all, there is a relationship. Now, some teachers might teach you it like this. You might say NP on NS, number of turns in the primary over number of turns in the secondary, is voltage in the primary over voltage in the secondary. And then they come and they tell you this, I secondary over IP. Now, personally, I've never liked this, right? I've never liked this equation when I was in Form 5. I still don't. So what I do when it comes to current and voltages, I see it in terms of power input and power output. That's how I see it. So your primary current by your primary voltage, that's your primary input power, is equal to the output power, which is the secondary current multiplied by the secondary voltage. Okay? So you want to work out your secondary current. So if I rearrange this formula here, your secondary current is simply going to be equal to IP multiplied by VP, right, all over VS. That's what you want to work out. So IP, you know what IP is? Where is IP? IP is 1.8 multiplied by VP on VS. Now this is where students make a little mistake here in this particular question. So VS on VP, VS over VP is, in my case, 8.91, right? So if you look at what you need to work out, you need to have VP over VS. So what you all have to recognize here is that that is actually 1 divided by 8.91. You have to invert that, right? Because what you have here is VS on VP, but according to my equation, I want VP on VS. So if you want to fix this, then we're just going to invert this, right? That's what I'm doing here. So we just need to work this out. So that's going to be 1.8 multiplied by open brackets 1 divided by 8.91. That. And I'm getting 0.20 amps. Okay. I don't know if anybody else worked it out. Yeah. So I've seen some people getting 0.2 amps. Great. Okay. Right. And then the last part here, if they do bring transformers as your data analysis, honestly, that's going to be an easy question, right? Okay. You want to calculate the power output of the transformer given that the voltage in the secondary is 55 volts. So power output is simply going to be your secondary current, IS, multiplied by VS, secondary voltage. Now your secondary current, we just calculated that we got 0.2. Sorry, wait. Yeah, 0.2. So that's 0.20 multiplied by the secondary voltage, which you're telling us here is 55. So that's going to be 0.2 by 55, and we're going to get 11 watts. Okay, so that's our power in this case here. Right, so I saw some of you all talking about radioactivity. Let me give you a piece of advice. Radioactivity, right, comes in the exam almost every single year. It comes in the exam almost every single year, and it is the shortest thing to revise for. So if you're running out of time between now and tomorrow, learn radioactivity, right? And that is physics of the atom. So now to draw the atom, know the charge and the mass of the particles that make up the atom. Make sure you know the J.J. Thomson, the Geiger-Mason experiment. Make sure you know the observations and the conclusions, and make sure you know how to calculate half-life. Okay. All right. So that's number 1. So number 2 in this paper here. All right. So we have a table here. We have complete table 2 by inserting the appropriate physical quantities and derived SI units. So first of all, we have volume. The derived SI unit for volume is going to be meter cube, right? When it comes to kg per meter cube, this here has to be density. We have Newton here, right? Force is measured in Newton. And then they want 2 units for derived SI units. So first of all, when we speak about derived SI units, so pressure can be measured in force per unit area, which is Nm to the minus 2, right? That is pressure, right? Now, for a question like this here, pressure is also measured in Pascal as well, right? Measured in Pascal as well, right? You all right with this? right? So I have a little time this evening here, so I might go a little longer, right? I'll go a little longer. So I know some of you all want to know when I'm going to finish. I normally have Form 5 maths class today, but that exam is over. Okay, the concrete block. So you have a concrete block here, and it is made with cement. And we want to calculate the density of the concrete block given that the mass is 20,160. So first of all, you all need to know that density is equal to mass over volume. That's the formula we're going to use. And you want to, you know, the mass is 20,160, 20,160 divided by the volume. Now, we don't know the volume of the block here. So volume is equal to length by width by height. So your length will be the longest side, which in this case, we'll take it as 2. It doesn't really matter which one you take as which. So that's 2, and that's measured in meters. Multiply by the width. Now here's a catch here that CXC kind of gives students here. There are some students who like to just plug in numbers into a formula without thinking about the units that they use it. So first of all, you will notice that this here is measured in cm. But when it comes to volume, your dimensions need to be in meters. So to convert from cm to meters, we have to divide by 100. So if you want to convert from cm to meters, we're going to divide by 100. So in this case here, if we divide by 100, you're going to get 1.4 meters. So that's the first mistake some students will make, forgetting to convert this here. So this is 1.4 multiplied by the height. The height in this case here is going to be 3 meters. So this is going to give us 2 by 1.4 by 3. Right? So that's going to give us 8.4. And that's 8.4. Since we work it in meters, it'll be meter cube. So this is going to be divided by 8.4. And that's going to be 20,160 divided by 8.4. And you're going to get 2,400. And because it's density, it has to be in kg m to the minus 3. Now, just for your knowledge, right? Just for your knowledge here, you will notice that CXC is giving you 4 marks here. This is how CXC marks a question. 1 mark for using the correct formula, 1 mark for substitution, right? And 1 mark here. Now, what they're going to do here, they're going to give you a mark for this, but they're also going to give you a mark for actually calculating the volume. So that's how they're going to mark a question like this. Okay? All right. We have a definition here. All right, so you want to define pressure. You don't want to lose marks in the exam for definitions. So pressure is the force acting normally per unit area. So pressure is the force acting normally per unit area. Now here's the thing, right? If I have a flat surface like this, right, and I have a force acting here, that force is acting at 90 degrees to the surface, and this here is my area, then the pressure is given by F over E. So let me give you a little trick here. If in the exam you cannot remember definition, if you remember the formula, what you can do is to write down the formula and just explain to them what each one of those things mean. So if you put P, say pressure, put F, say force, and if you have E, call it area. Okay, that's basically what we do. Some of you all said perpendicular to the surface. Yeah, that could come too, right? It's fine. All right, let's see what's happening here now. Next one. So they want us, right, calculate the pressure exerted on the floor by the base of the concrete block. So first of all, pressure is equal to F over E. You all need to recognize that. Now to calculate the force of the block, right, so you have a block here. Now the block has a mass, this is mass here. So first of all, if an object has mass, it is going to have a weight, which is given by m by g. So we're just going to take the mass of the block, which is 20,160. And we're going to multiply by g, which is 10. So this is going to be 201,600 newtons. Okay, so that's the weight of the block here, 201,600. And we're going to divide that now by the area. But the area that you are concerned with here is this area here. See, this base at the bottom here, this piece. Right? This piece is what you're concerned about. You need to work out this area here. So that area is simply going to be, since it's a rectangle, we need to take 1.4 and just multiply by 2. So this area here is going to be 1.4 multiplied by 2. So when I work this out, I'm going to get right, you're going to get 72,000 Pascal. Right, so you can put Pascal here, or you can put Nm to the minus 2, right, or Pascal. Okay. Right, so that's number 2. Now if they bring thermal physics looking like this, right, this is going to be a breeze for some people. It is usually pretty straightforward. So this is the third question on the paper here. They want you to define heat capacity. Now be careful, because sometimes they can ask us heat capacity or specific heat capacity. So heat capacity, right, is the energy, right, needed to raise the temperature of a substance by 1 degree. Right? So that is what heat capacity is. So in terms of symbols, we have a big C to represent heat capacity. You all need to know the relationship between heat capacity and specific heat capacity. So there is a formula that relates heat capacity to specific heat capacity. So this here is heat capacity, that's a big C. Right? This is mass, obviously. Right? And this one here is specific heat capacity. Okay, now define the term specific latent heat of vaporization. So when we speak about latent heat, and we're talking about vaporization in this case here, you are taking a liquid, right? You're taking a liquid and you are converting that into a gas, right? So whatever temperature you are at here, so let's say you're at a particular temperature here, when you convert that into a gas, you are at that same temperature as well. So specific latent heat of vaporization is the energy required to convert 1 kg of a liquid into a vapor or gas without a change in temperature. Now here's the thing here. This is 3 marks here. You see, if you all leave out that last piece there, if you leave out this piece here, you're going to lose a mark, eh? Just letting you know. You must indicate this here, without a change in temperature. That's part of your definition. It is required. Okay? All right, so what else we have in this question here? Chances are we're going to have a calculation. So while I'm getting the next part here, guys, feel free to share the link to this live with your friends, right? Please remember to hit like and subscribe. Trying to help you all out here. You all help me out as well, right? Try to promote my channel as well. Okay, so a substance which has a freezing point of 80 degrees is cooled from 90 degrees to a total solid at its freezing point. Sketchy graph right, to represent this here. So first of all, some of you all may have done a cooling curve as a physics lab in school. So they told you what the melting point is. So all I will do here, if I have to do a question like this, I will draw a dashed line here to represent your melting point, or your freezing point in this case here. So we started off at 90. So when you start off at 90, the object's temperature is going to drop. But as soon as the object starts to turn into a solid, you're going to have this flat line section here. And if we continue cooling, you're going to do this. Okay? So this is a typical cooling curve here that we are drawing. That's it. Okay? All right. What else we have here now? Some calculations. All right. So a student conducted an experiment in which 1.5 kg of water at 30 degrees was converted to steam at 100. Okay? Assuming no heat loss to the surroundings, calculate the energy needed to heat the water from 30 degrees to 100 degrees. So first of all, if you have water, and what I normally tell my students to do is to draw a simple diagram so we can visualize what's happening here. So we have water, and we have 1.5 kg. So 1.5 kg. We have water. Right? And the temperature of the water here is 30 degrees Celsius. What I want to do, I want to take that same water and I want to figure out how much energy is required to bring it to 100 degrees here. So again, what's going to happen here is that we still have the 1.5 kg of water. Nothing, the mass hasn't changed. We still in the water phase or liquid phase. But the only thing that happened here is that our temperature is now 100 degrees Celsius. Whenever you just have an increase in temperature, the formula that you're going to use is E is equal to mc delta theta. That's the formula that we're going to use. If we are just increasing temperature, that's the formula you're going to use. Now, a common question that I get from students, or have gotten from students over the years, when they see me do the calculation, why did I not convert to Kelvin? So first of all, let me tell you, when it comes to the gas laws, that is the only time that you're going to convert your temperature into Kelvin. That's the only time you're going to do that. Okay? So just be aware of that. Do they give you, yeah, so somebody's asking about the values. Yeah, in the question, they're going to give you the values. So I'm gonna refer to what they give me in a sec here. So first of all, let's work out part one. So the energy required to raise the temperature of this water here is going to be mc delta theta. That's the formula we use. So the mass of the water is 1.5 kg multiplied by C. Now, let me just show you what they gave me in the question. They gave me some information. Right? You don't need to learn off specific heat capacity or latent heat of vaporization. They will give you those things in the exam. It's there. If you're not seeing it, go to the end of the question. That's where this one was. So C is 4200 multiplied by delta theta. Now, we're only concerned about the temperature change. I get this question a lot sometimes. Some students say, well, we're using final minus initial. Honestly, I don't really care if it's initial or final. All I'm concerned about is the difference. What's the difference here? So in this case here, going from 30 degrees to 100, that's a change of 70. That's a change of 70. So in this case, I'm just going to take the bigger number minus the smaller number, right? And we're going to work this out here. So this is going to be 1.5 multiplied by 1.5 by 4200 multiplied by 70. And I'm getting 441,000 joules. Okay? If anybody else working it out, let me know. All right. So again, once we're trying to work out an increase in temperature, we're simply going to use the formula E is equal to mc delta theta. Okay? All right, somebody's asking, do we need to convert to standard form? Yeah, you don't need to convert to standard form. You don't have to, right? You don't have to. Okay. All right, so that is part one. What do you have for part two here? So in part two, they want to convert the water into steam. All right, so let's understand what's happening here now. So first of all, we want to convert the water at 100 into steam at 100. So if you have water, right, and this water here is at 100 degrees Celsius, and you want to convert that into steam, right? So this is steam here, and this steam here is at 100 degrees Celsius. So when you think about it, what's happening here? So we are trying to make this change here. So you have a phase change taking place there. Once we have a phase change taking place, the formula that we're going to use is E is equal to ml. But because we're going from liquid to gas here, it is going to be mlv. So that's the formula that we're going to use for a phase change. So we're going to say E is equal to m multiplied by L by V. I think the mass was what? 1.5. Yeah, 1.5 multiplied by LV. And LV in this case here, they gave us that in the questions right here. 2.3 by 10 to the 6. So in this case here, that is going to be right. And we could write this one in standard form here if you want. That's 3.45 by 10 to the 6 joules. All right. Okay. Right. And the last part of the question, right? Last part of the question here. They want us to work out for 1 mark. Right? They want us to work out this last part here. And if you all seen it, they said the heat, right? Heat the water from 30 to 100. So if you remember what started off, we started off with the water. The water was initially at 30 degrees Celsius. Now we took that water, we converted or we increased the temperature of the water, we reach 100 degrees Celsius. Then the next thing happened now is that that water is converted into steam at 100 degrees Celsius. Okay, so in this case here, all we need to do, we need to take this energy change and we need to add that to this energy as well here. So the total energy required to make this change will be the answer we got before, which is 441,000. All right, plus we're going to, I'm going to add this answer, 3.45. Okay, when we add that up, we're going to get right? So you can write this in standard form if you want as well. 3.891 by 10 to the 6 joules. Okay, it's only 1 mark for that, so CXE. Okay, so that is number 3rd question. All right, this next one here is on ray optics. So it says 3 features of an image produced in a plane mirror. Anybody know what are the features of the images or the image produced in a plane mirror? right? So, yeah, seen some answers coming through here. So first of all, we're talking about the image produced in a plane mirror, right? So you guys, you wake up in the morning, you go to brush your teeth. So you might stand here in front of your mirror, okay? And when you look in the mirror, you're going to have an image. So the image is going to be on the right-hand side here. So let's say we have an image here. And we want to know what are the features there. So first of all, when it comes to features, so the image produced, so this is, if this is your object, and this here is your image, it simply means that you are forming an image there, but that image is virtual, right? So it's a virtual image here. Now CSEC can ask you guys what is meant by a virtual image. A virtual image is simply one where the rays appear to pass. It is one where the rays appear to pass, and also it cannot be formed on a screen. That's what a virtual image is. Okay, the rays don't actually pass through it, and it cannot be formed on a screen. Okay, the second feature, let me see what you all said here. The second most obvious feature is that it is laterally inverted. Okay, it is laterally inverted. Right, it is laterally inverted. Now, when we speak about lateral inversion, it's as if I hold up my right hand, when I look in the mirror, it appears that my left hand is up. That's lateral inversion. And the third feature, right? We have to put our third feature here. You can say something like the object distance. Right, is equal to the image distance. Right, there are a few more things we can say here as well. Huh? So we can say that the image is upright. Right, so the image is upright, and you could talk about same height. Image and object is same height. So there are other possible answers here. Okay. What else do we have here now? On some calculation, hopefully. Oh. Right, so they want us to, so we have a diagram here. It shows a ray. So first of all, this is a concave lens or divergent lens, and we want to complete the ray diagram. So first of all, when you have a ray that is parallel to your principal axis and it's passing through a divergent lens, we know the ray is supposed to do this, right? We know the ray is supposed to do that. But what is supposed to happen is that when you extend that line backwards, that line is supposed to pass through your focal point. That is what's supposed to happen. So they say complete the ray diagram. That's it. That's what's going to happen, right? Showing the part of the ray after it passes through the lens. That's it. So 1 mark for, well, 2 marks for that. The next thing here on the diagram, we want to label the focal length. So the focal length of any lens is simply the distance between the optical center of the lens and your focal point. So this here is F. That's your focal length of a divergent lens. If CSEC had given us a question about a convex lens or convergent lens, it'll look like this. You have a ray passing through the center of the lens, and let's say you have a ray that is parallel. What is going to happen is that that ray is going to pass through, it's going to converge, but it's going to pass through what we call the focal point of the lens or the principal focus. Again, if you want to work out or you want to define your focal length will be from here to here. That's your focal length. Okay? So I've seen questions where CSEC asks us to define focal length using a convergent lens or divergent lens. So we need to know both of them. All right, this next one here, we're going to use the lens formula. So we have an object AB placed 15 cm in front of a lens. So first of all, your lens formula looks like this. 1 over F is 1 over U plus 1 over V. That's our lens equation or lens formula. So first of all, what do we know? So the object is 15 cm in front of the lens. So U is equal to 50. That's your object distance. The focal length is 5, so F is equal to 5 cm. And we want to get the image distance. So you're trying to calculate V, we don't know what that is. So we're going to substitute into that formula. So we're going to say 1 over 5 is equal to 1 over U, which is 15, plus 1 over V. So now this is a maths problem now. It's no longer a physics problem. So 1 over V is equal to 1 over 5 minus 1 over 15. So therefore, 1 over V is equal to, so this is 1 over 5 minus 1 over 15. And we're going to get 2 over 15. Right? Now that there is not the answer. V now is going to be, you have to invert this. V is going to be 15 over 2. So therefore, V is 7.5 cm. Right? So that's your image distance here. Right? Somebody say I missed A part 2. Which one is A part 2? Right? Oh, okay, yeah. So some of you are saying I'm miss A part 2. So I'll show you in a sec what that is. That's straightforward. Right? That's straightforward. Okay, I'll just finish up this piece here and I'll go back to A part 2 for you. So first of all, this is your image distance, 7.5. What else we want? Oh, they want the magnification. Right, so this is the second part here. They want you to calculate the magnification. So there are two formulas for magnification. Magnification is simply going to be V over U. So V in this case here is 7.5. And we divided that by U. U is 15. Right? So 7.5 over 15 is going to be a half. So therefore, your image is going to be smaller in this particular case here. All right? So that's your magnification is going to be a half. Okay, so the piece that you are saying that I miss out is this piece here. Explain why the word police is painted in this manner at the front of some emergency vehicles. So first of all, if you are driving, so let's say you're in a car here, right? In a car here, and you have a side mirror here, right? Well, I didn't know that drawn properly. All right, you have a side mirror sticking out on the side here, side mirror sticking out on the side here, right? And this is your car. It's a top view of the car, right? And you have a police vehicle in the back here, right? And the police vehicle is approaching the car. So we just learned that when it comes to a plane mirror, lateral inversion takes place. So what is going to happen is that if I am a driver here and I look into my mirror and you have the word police here written in front of the police car, what is going to happen is that the mirror is going to laterally invert it. When it does that, what I see, I'm going to see the word police correctly. Okay, so that's the purpose of writing the words backward on your police vehicle here. Okay, so you basically have to explain that in words. You need to speak about the mirror. You need to speak about lateral inversion. And when you, as the driver, look into the mirror, the word police is going to be seen correctly. Okay. Right. Question 5 here. All right, so a semiconductor diode is used for half-wave rectification. So first of all, when it comes to current, there are two kinds of current, and this can come in the exam as well. So we have something called direct current, and we have something called alternating current. So direct current, the electrons flow in one direction only, and your current literally flows in one direction only. So a normal dry cell, the current will be direct current. When it comes to alternating current, the flow of the electrons reverses direction regularly with time. That is what an alternating current is. That is an exam question. What is the difference between AC and DC? So direct current, electrons flow in one direction only. Alternating current, the current or the electron flow reverses direction regularly with time. That's what's happening. Okay. So in this case here, they want you to draw the IV characteristic for a semiconductor diode. So this here is I current in amperes, V voltage. So first of all, the symbol, the circuit symbol for a diode is this. You all need to know that, right? That's a semiconductor diode. And what a semiconductor diode does, it allows current to flow in one direction only. So a diode will allow current to go only in that direction. What I tell students to do is to look here. There's an arrow that tells you the direction it should be moving. So current will flow that way. If I try to push a current through the diode in the opposite direction, think of this as a barrier. It is blocking the current from going. Okay? So this is how you figure out how the current is going to flow through a diode. Now, in terms of the graph though, so the diode will not allow any current to flow when it's reverse bias. So there's no current here. Then what's going to happen is that the diode turns on about here so, and we get a curve. It is not a straight line. So therefore, a semiconductor diode does not obey Hooke's law. Ohm's law, right? It doesn't obey Ohm's law. There are two other graphs you need to know for the exam. So one of them is the IV characteristic for an ohmic conductor or resistor. If I plot a graph of I against V, what I'm going to get here is a perfect straight line. So this here is for an ohmic conductor. All right, that's one graph you have to know. There's a second graph here. And this one here is for a filament lamp. So if I were to plot I against V, then the graph looks like this. It's non-linear, right? It does this. So CSEC can ask you to draw this graph here. This is for a filament lamp. And I know some of my students would have done this as a lab in their schools. So this graph is also non-linear. CSEC can ask you to explain why the graph does that. And all you need to tell them is that when the temperature of the bulb increases, its resistance also increases. Okay? When your temperature increases, your resistance increases. Okay? All right. What else we have here? That's part A. Right, part B, they want me to complete the truth table for a NAND gate. Okay, now logic gates, if it does come in the exam, is going to be very easy. So let me just give you a quick review of what you need to know for the exam. So there are 5 logic gates you have to know for the exam. 5 gates. And these are the 5 gates. So the first one, this particular gate here is called a NOT gate. A NOT gate only has one input and one output. So if I have to draw the truth table, we're only going to have 2 possible options. It could either be a logic 0 or a logic 1. Those are the only 2 options that can go into that input A here. Now a NOT gate is referred to as an inverter. Now so for those of you who don't know, I am an electrical engineer by profession, right? And when it comes to logic 0 and logic 1, in actuality, we could be looking at voltages. So a logic 1, so inside a computer, a logic 1 could be a plus 5 volts. Logic 0 could be either 0 volts or it could be minus 5 volts, right? So when we speak about logics is just about a concept, but in actuality, it could be a voltage. So first of all, I'm saying that this here is called a NOT gate. So you'll need to know the symbol for a NOT gate, and you need to know what we call the truth table. The truth table tells us how the logic gate works. So if a 0 comes in, you're going to get a 1 coming out. And if you have a logic 1 coming in, you're going to get a logic 0. So simple truth table here, that is for a NOT gate. We also need to know the truth table for an AND gate. Now the AND gate looks like this. We have 2 inputs. We have an input A, input B, and the output is C here. And this is called an AND gate. Now when it comes to an AND gate, you have 2 inputs. So you have A and you have B. And the output in this case is C here. Now, because you have 2 inputs, the number of combinations for this logic gate is going to be 4. There's a formula, right? You all have to know the formula, but the formula is 2 to the power n. That'll give us the number of inputs. Right? So for the NOT gate, you have 1 input. So therefore, we have only 2 combinations. But for an AND gate, we have 2 inputs. So therefore, we have 2 to the power 2. So we have 4 in total. Now these four here, I need you all to write this in the correct order. So it's 0, 0, 0, 1, 1, 0, and 1, 1. I am counting in binary here. Okay, so we're using this exact same numbering. Don't go in the exam and mix it up, you know, because when the examiner trying to mark it and he getting confused, right, that'll be a problem, right? Right, some people say they never learn that formula. Yeah, that you don't need to know the formula. I'm just telling you it, right? In terms of my background, you all know I wrote the E-level physics books, right, for CSEC. That's on the syllabus, right? So yeah, there's a lot of information that I know. Okay. So first of all, we want, right, so that's the truth table here. Now here's what you need to remember for the AND gate. So to remember the AND gate will only have an output of 1 when you have a 1 and a 1. That's all you need to remember. You need to have a 1 and a 1. So you're going to put a 1 here, and then you're going to put zeros for everything else. That's all you need to remember. For the AND gate, it must be a 1 and a 1. That's all you need to remember. Okay? The other gate we need to know is what we call the OR gate. So this is what the circuit symbol for the OR gate looks like. So this is A, this is B, and this is C here. So this is called an OR gate. So again, you have two inputs. So let's draw the truth table. So we have A, B, C. Again, because you have two inputs, the combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Let me just make sure you all see my screen here. Yeah. So here's what you need to remember for the OR gate. So for the OR gate, the output is 1 if you have a 1 or anything else. So therefore, you're going to get a 1 here, a 1 here, and a 1 here. And therefore, this is going to be a 0. So these are the three basic gates that we first must understand, right? We must understand that first. Okay. Now, remember at the beginning I said we need to know 5 tables. So you can create something called a NAND gate, which is really made up of an OR followed by a NOT. So this here represents the circuit symbol for a NAND gate, right? It's called a NAND, right? It's a NAND gate. So you have two inputs again. So let's go A, B, C. So in terms of combinations, we're going to have the same set here. So it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. So first of all, you need to understand that the NAND gate is the exact opposite of the AND gate. So whatever was happening with the truth table for the AND, you're just going to reverse it. So therefore, this is going to be 1, 1, 1, 0. That's it. Okay? So it is the exact opposite of your AND gate. And then we also have what we call the NOR gate. So the NOR gate looks like this. All right, so we have A, we have B, and we have C, and it's called a NOR gate. So again, with the NOR gate, the combinations will be the same again. So this is 0, 0, 0, 1, 1, 0, and 1, 1. So the NOR gate is the opposite of the OR gate. So this will be 1, this will be 0, 0, and 0. So there are 5 logic gates you all have to know for the exam, right? 5 of them. Yeah, NAND means not and. That's what it means, right? Right? So let me give you one simple thing here. All right. Let's do a combination. Let's see. So let's say I have an AND gate here. I have A, I have B, and let's say we have a NOT gate here. C. And we take both of them and we pass that through an OR gate. Right? So CSEC can give you a combination of logic gates. And honestly, if you get a question like this, there's free marks in the exam. Honestly. Okay? A, B, C, D, E, and F. Now, when it comes to the truth table, we need to make sure. So CSEC can ask you, they can give you a truth table and ask you to complete, or you could be asked to complete the truth table. So first of all, if you notice here, we have 3 inputs into this logic combination. Now I just give you a formula there that says 2 to the power n. So if you have 3 inputs, I expect to get a total of 2 by 2 by 2. That's 2 to the 4 to the 8 combinations, right? So there are 8 possible combinations to work out here. So first of all, let's draw up a tree table. So we have A, we have B, we have C, we have D, we have E, and we have F. So again, CSEC may just give you a table, but if I don't have a table, I have to be able to come up with it as well. So first of all, let's look at combination AB. Now, since you have 2 inputs to that AND gate here, your combinations are 0, 0, 0, 1, 1, 0, 1, 1. So there are 4 different combinations for those inputs A and B here. Now, you're going to mix C in the mix here. So therefore, let's put all of them equal to 1. Let's say all of them equal to 1 here initially. Then what we're going to do, we're going to write over the combinations now. 0, 0, 0, 1, 1, 0, 1, 1. But this time, you're going to switch off this here. Make sure these are zeros here. So when I check it here now, you realize we have a total of 4 plus 4. So you get your 8 combinations. All right. So even if CSEC doesn't give us the table, we can actually come up with the table as well. Okay. Like I said, this is easy marks in the exam if it does come, right? Free marks here. So first of all, I could work out, let's see, I'll probably work out E first. That's the easiest one. You're passing through a NOT gate. So you're looking at C. So we're looking at this column here to figure out what we put in here. So if this is a 1, it means all of this here will be zeros. Then if all of these are zeros, this will be 1, 1, 1, 1. Okay? So I have E completed. I need to work out D now. What is E dependent on? Sorry, what is D dependent on? This D here is dependent on A and is dependent on B. Now, it's an AND gate. The only time you're going to get an output of 1 is if we have a 1 and a 1. So you'll get that here and you'll get that here. So therefore, everything else should be 0. So this is 0, 0. This is 0, 0, and 0. That's it. So we almost finished. The only thing we're missing now, we need to figure out what's happening to F. So let me use a different color here for F. So in this case here, if you want to figure out for F, what are we going to look at? So the input to F would be D and E. So all we're concerned about, we're looking at this and we're looking at this here. So this here, this gate here is an OR gate. So you all remember that for an OR gate, the output is 1 if you have a 1 or anything else. So the first thing I will do, I will try to figure out where do I need to put 1s. So if I'm looking at D and E, I'll put a 1 here. I'll put a 1 here, a 1 here, a 1 here, a 1 here. This will be 0, this will be 0, this will be 0. Easy 8 or 6 marks in the exam if it comes, right? Right? So I noticed some people asking, what is this? Right? Guys, if you do know what this is free marks in the exam. That's what it is, right? So I'm not going to spend too much time on this. You all need to know these 5 logic gates, and they could ask you a combination, which is what I've done here. Okay? So let's go back across here. This is what the question was. For 4 marks, they want me to complete. It's a NAND gate. So if it's a NAND gate, it means it's going to be the opposite of an AND gate. So therefore, this is going to be 0, this is 1, this is 1, this is 1. I get 4 marks here, just like that. Okay. All right, let's see what else we have here now. Right, this paper had some easy questions. All right, so we have 3 resistors here. We have a 2 ohm, we have a 5 ohm, and a 10 ohm, and we want to calculate the equivalent resistance. So first of all, these resistors are connected in series. So for series resistance, the total resistance is R1 plus R2 plus R3. Okay, so first of all, R1 is 2 plus R2, which is 5 plus 10. So that's 10 and 5, 15 and 2, 17. So this is going to be 17 ohms. 3 marks in the exam for this question here, right? So I don't know what CSEC was thinking. The next one here, maybe I could put it here. Actually, no, not here. For this next one here, we have resistances that are connected in parallel, right? They are all connected in parallel. And we want equivalent resistance. So first of all, for parallel resistance, we say 1 over RT is equal to 1 over R1 plus 1 over R2. So 1 over RT is equal to 1 over, now in this case you have 3 resistances, so you could put an extra resistance inside it. So 1 over 2 plus 1 over 5 plus 1 over 10. Okay, so therefore 1 over RT is equal to, so we're going to add up a half plus 1 over 5 plus 1 over 10, and you're going to get 4 over 5. So therefore RT is equal to 5 over 4, right? This is 1 1/4, which is 1.25 ohms. Okay, so that's how we calculate resistance in parallel. Okay. Right, some of you all asked what paper is this? This is May 2019, right? May 2019. Right, and the last part of the question, they said the resistors in figure 8 were connected to a 6-volt power supply. So first of all, the resistors in figure 8, so that's the parallel resistor combination here. So first of all, you have this here, 3 resistors. Right, so we have 3 resistors here, 2, 5, and 10. Right, and they're all connected, so they tell us that they are connected in parallel with a 6-volt power supply, right? So this is essentially what we have here, and we want to calculate what is this current here flowing in the circuit. So first of all, this here, the resistance, we could have taken out all 3 resistance here, and we could have placed 1 resistor, which is actually this value that we calculated here. So when you all calculate RT, that's the combined resistance in the whole circuit here. So this is going to be 1.25 ohms, and that there is really connected to a 6-volt power supply. Okay. So this here is the current we're trying to work out. This is 6 volts. So all I need to do, if I have a simple circuit like this and I want to get I is simply going to be V on R, which is going to be 6 volts over 1.25. Okay, so this here is going to be 6 divided by 1.25. And this is going to give us 4.8 amps. Okay, so that's our current flowing in the circuit. Right, some people say what time we ending. I will try to go as long as I can, right? Not till 2 o'clock in the morning, not doing that. Right, I'm just trying to help out as much students as I can. I know my class should be as ready as they can be for the exam. Generally, more than half my class get grade 1s. Last year, 95 of my students got grade 1s in physics. Okay, and I had a student, she placed second in Jamaica last year. So we have lithium. Lithium-7 is an isotope of lithium. It has a mass number of 7 and atomic number of 3. So we have Li, mass number is here, atomic number is here. Now, the question wants us to see how many protons we have and how many neutrons we have. So in terms of protons, protons is simply atomic number. So it's going to be 3. To work out the number of neutrons, we take the mass number and we subtract the atomic number. So we get 4, right? Easy marks here. Now the next part, they want me to draw a clearly labeled diagram, the structure of a lithium-7 atom. All right, so first of all, when it comes to physics and chemistry, we have a slight deviation from what we actually do. So Li, it is 773, right? That's the isotope here we're talking about. So first of all, let's write out the electronic configuration using the atomic number. So a 2 is going to fill in the first shell, and then 1 is going to fill in the second shell. That's it. You have 3 electrons to fill here. So we already know we have 3 protons. We already know we have 4 neutrons. And based on the atomic number, we know we also have 3 electrons. Okay? So let's draw this thing here. So first of all, you can place, you're going to place where the particles are in the atom. So inside the nucleus, we have protons and neutrons. So you're going to do this. You're going to say 3p here for protons. You're going to say 4n for neutrons. And let's enclose this here. Okay? Now this is physics, not chemistry. So you're not going to put Li in the middle here. Physics is concerned about what particles are present inside the nucleus. So now I'm going to draw the first shell. I'm going to leave this circle here to represent the nucleus. And now I'm going to draw the first shell. Okay? So this first shell here, we are going to put 2 electrons. So you're going to put X here, X here. So that's 2 electrons. We're going to draw a second shell here. Right? So this second one here, we are just going to put 1 electron. So we're just going to put 1 electron here. Now, when you're labeling a diagram like this, now it's 4 marks. So make sure you put everything here. You're going to say this is the nucleus. Right? You're going to tell them that P represents protons. Right? You're going to tell them that N represents neutrons. Right? And you're going to use the X here to represent electrons. Okay? So this is a complete diagram here for a lithium atom. Okay? Right? Okay, so next thing. So almost every year we get a question on half-life, so make sure you know how to do half-life. So in 4 days, the activity of a sample of lithium decreases to 1/16 of its original value. Define the term half-life. Now I see students struggle with this definition, and I'm not sure why. So half-life is the average time taken for the activity of a sample right? Or you can say radioisotope to decrease time to complete activity of a sample to decrease right by half its initial value. Right, so this is what half-life is, right? That's what half-life is. Make sure you know that definition. Now the next part here is to calculate the half-life of the lithium. Okay, so they gave us some information here, and they spoke about the activity decreasing to 1/16 its original value. So this is 1/60. Whenever we start speaking about fractions here, all you need to do is start off with a whole. So 1 is the original amount, and let's start decreasing this thing here. After 1 half-life, we expect to get half. So this here corresponds to 1 half-life. Every arrow is a half-life. If we decrease by half again, this turns into a quarter. So that's a second half-life that we've gone through. And then if we decrease this by 2 again, right, you're going to get 1/8. So that's another half-life. And if we go again, right, if we decrease this by 2 again, this is going to be 1/60. So that's a third half-life. Now, all of CXC's questions are going to follow this format. They're not going to give us a complicated formula for half-life. That's for A-level physics. So in this case here, what they told us in the question, they said, in 4 days, right, it took 4 days for this to happen. So what's happening here is that you're starting off with this amount. That's the original amount here. And then what's going to happen is that it decreases to reach this here. And this takes 4 days. Right? That takes 4 days. So when we look at the diagram though, the amount of half-lives we went through would have been 1, 2, 3, and 4. So therefore, 4 half-lives is actually equal to a time interval of 4. This 4 here. So therefore, your half-life for this lithium here is going to be 4 divided by 4. So therefore, your half-life is going to be 1. And this time was in what? Time could be in seconds, it could be in hours, it could be in years. 4 days, right? 4 days. So the time we're working with in days, so this is going to be 1 day. Right? So that's our half-life for this sample here, 1 day. Okay, we just have one more part to this question here. All right, so we want to calculate the energy given off in a nuclear reaction if the change in mass is 0.2014. So first of all, the formula that we're going to use to calculate the energy change in a nuclear reaction is mc squared. All right, up to primary school children heard about this before, so you all shouldn't get this wrong. Okay, so in this case here, equal mc squared, we need mass, but you need to remember that mass has to be in kilograms. So first of all, they gave us the mass defect or the mass change in U. So first of all, 1 U is equal to, and they will give us this in the exam, 1.66 by 10 to the minus 27. So you're going to need this here if you want to convert from U into kg. So you're going to say 0.2014 U, and we're going to convert that into kg. We're just going to multiply this. We're going to say 0.2014 multiplied by 1.66 by 10 to the minus 27. And this here is going to be 0.2014 multiplied by 1.66 by 10 to the 27 minus. Okay, this is one of those questions here where we don't round up anything in the question. We're working with every single thing you see on the calculator. So 3.34324 by 10 to the minus 28 kg. Okay, so I'm not rounding off anything at all. I'm working with this whole number here. So that's a mass change in this chemical reaction. Sorry, this nuclear reaction. So this is going to be minus 28. And you're going to multiply by the speed of light squared. They gave us that in the question. It is going to be 3 by 10 to the 8 squared. So we just need to work this out here. So this is multiplied by 3 by 10 to the 8. And we're going to get, so generally I don't round up this at all, 8916 joules. Okay, so these are things that show up in the exam a lot. We need to make sure we know this. Okay. Yeah, somebody making a point there, bio and chem. Yeah, bio was so easy, chem was easy. So physics should be easy tomorrow, right? Let's keep our fingers crossed for now. All right, so that's June 2019. Okay. Right, so let's try our next one here, right? I'm working backwards because what happened with my Form 5 physics class, I would have started with the 2026 paper and I worked backwards. Okay, in terms of our preparation, we made it to, I think 2021 would have been the last papers I did with them. So I don't want to give them the same papers we did in class. So I'm gonna do May 2018 for you guys here, right? May 2018. Let's see what this one looks like. Right, so this here is May 2018. Right, I realize I'm blocking it. Okay, so in this question here, we're going to use a lens, we're going to use an XY frame, and we're going to use a screen in order to determine the focal length of a convex lens. So basically what's happening here is that they are varying the distance of the object from the lens, and then they're recording where the image is forming on the screen. So you have a table that is going to contain image distance and object distance. And then based on that, we're going to calculate the focal length. So let's see what we have to do here. All right, so this is our table here. All right, this is our table here. And we want to complete the table basically. Okay. Now with these kinds of questions here, they want us to complete the table. So they have U in centimeters and they have V in centimeters. But you will notice that they have a new column here, 1 over U, and they have 1 over V. CXC wants you to complete 1 over U and 1 over V to 3 significant figures. Okay, that's what it was. So first of all, for 6 marks, CXC is giving away free marks because they're basically telling you here what? Play with your calculator. That's what they do. All they're doing is saying, play with your calculator, right? You all definitely have to get this correct if it does come, okay? So in this case here, we're going to say 1 over 20. So I'm going to work out each one of these here. 1 divided by 20, you're going to get 0.05. Now they want to answer the 3 significant figures. So this here is actually 3 significant figures, in case you don't know. You all know in the maths paper, that question with the significant figures. The answer for that there to 1 significant figure would have been 4 alone, right? If you had put 4.00, that is not 1 significant figure. That is actually 3 significant figures. So in this case here, it is going to be 0.0500. Now we're going to do that for all of the data. So 1 divided by 30, we're going to get 0.0333. The next one is 1 divided by 40. You're going to get 0. Right? Next one is 1 divided by 50. You're going to get 0.0200. Then 1 divided by 60. You're going to get 0.0167. And then 1 divided by 70. You're going to get 0.0143. 1 divided by 55.6. We're going to get 0.0180. Next one is 1 divided by 30.2. We're going to get 0.0331. Then we have 1 divided by 23.8. Right, I forgot how long this thing takes to work out here, right? Right, and the last one is 1 divided by 19.2. I'm gonna get 0.0521. Okay, so that's my table there. That's my table for 6 marks here. Okay. Right. So yeah, you're asking what year this is. This is May 2018. Right, May 2018. Okay, so that's part A. The next part now, they said on the grid, we want to draw a graph of 1 over U against 1 over V. My suggestion to you is when you have to draw a graph, make sure you know exactly what you're plotting. So it's 1 over U against 1 over V. That's what you have to be plotting in. Now, first of all, we didn't complete the table because we had to give 1 over U a unit. So this would have been Cm to the minus 1. This here would have also been Cm to the minus 1. Because you're finding 1 over your image distance or object distance, it's going to be 1 over Cm, which is Cm to the minus 1. All right. We want to plot a graph of 1 over U against 1 over V. So let me get some graph paper. so this is my graph here. I'm going back to the same graph here because I want to borrow some, I want to borrow the axes. Okay. All right, let's get the table across here. When you're doing a question like this, make sure you have your table close by. And I think normally the graph paper is right next to the table, so it'll be okay. All right, so this is my data here. Okay, now just like the previous question there, we need to decide on a scale. You need to decide on a scale. So which one is which again? 1 over u is your y. So this is y here, and this is going to be x. So make sure we don't mix them up. That's what we're going to plot. Now we need to figure out what scale are we going to use. So first of all, this is 1 over v. And that's going to be in cm to the minus 1. And then across here, we have 1 over u. And that's cm to the minus 1. Now in terms of the scale, because you're getting marks for a scale. So on the x-axis, right, and the y-axis. All right, so if we look at the x-axis here, we're going from, so we can probably do this, 0, 0 0.01, 0 0.02, 0 0.03, 0 0.04, 0 0.05, and then 0 0.06. So on the x-axis, we can use 2 cm to represent 0 0.01. For the y-axis, based on the numbers that we have here, we can use the exact same scale. So this is going to be 0.01, 0 0.02, 0 0.03, 0 0.04, 0 0.05, 0 0.06, and how far we go down? We could probably stop right here, but 0.07. Okay, so on the x-axis and the y-axis, we're using the exact same scale. So represent 0 0.01. Okay. Okay, so let's see what's happening. So we need to plot these points here. So first thing we're going to do, we're going to plot 0.18 against 0.05. So 0.018 against 0.05. 0.018. So that is going to be about here. Right? Now you're getting a lot of marks for plotting the points, so you have to be as accurate as possible. The next one here is 0.033. 0.033. Against 0.033. So this is going to be 1, 2, 3. That's about here, right? The next one now is 0.042 against 0.025. 0.042, that's for 142. Right, that's here. The next one is 0.045 against 0.02. That's going to be here. The next one is 0.05 against 0.017. That's somewhere here. And the last one is 0.052 against 0.014. Right, that's right here. So as you can see, right, there seems to be a straight line. And this straight line graph here obviously is going to have a negative slope. So again, we have to draw this in such a way. Right? Now remember, you're trying to balance your points here, right? As we're trying to balance the points about this thing here. Okay? So this could probably be 1, 2. Right? This looks like a possible graph here, right? Probably. Okay. So this here represents my graph of 1 over u versus 1 over v. Okay. I'm sure the next thing they're going to ask us is for the slope. Yep. All right, so in this case here, we want to calculate the gradient of the graph, and I want to answer to one significant figure. Okay, so let's go back to the graph here. Like we did previously, we are going to select 2 points on the graph, and my suggestion is always select points that you can actually read off from the graph. So for this one here, I'll probably choose this here. This is A, and I could probably use this a nice point here as well. This is B. So select 2 points that are easy to read off. That's the objective, right? Always select points that you can read off easily from the graph. So let me borrow my dash lines from across here. All right, so let's put our line here. Again, CXC is giving you marks for completing this right angle triangle. So please make sure to put it in, right? Okay, so to work out the slope here, let's write down the coordinates of A and of B. So A in my case here is 0.01. So A is 0.01 against, this is 0.056. That's 0.058. That's what that looks like me. 0.058. And my B here corresponds to 0.06 against 0.005. Okay, so I have the points here in order to work out my slope. Can you all work out the slope for me here? Can you all work out this slope for me? All right, just put your answer in the chat there if you work out the slope for me, right? The question says they want the slope to one significant figure. Again, -0. Casio calculators, yeah, hopefully, hopefully. Right, honestly, if I were you and I had the Sharp and I had the Casio, I'll work with both of them. In case they give me trouble, I have the Sharp to fall back on. Okay, I've seen some people getting -1, -1.06. So here's what I'm going to do here. I literally gave you the points that I'm going to use. So if you want to work out the slope, m is equal to y2 minus y1 all over x2 minus x1. So we're just going to substitute into my formula. So to do that, let's label this thing here. x1, y1, x2, y2. So in this case here, y2 is 0.005 minus 0.058 all over 0.06 minus 0.01. So when I work this out here, I'm going to get right? This is what I'm getting here. I'm getting -1.06 as my slope here. But the question says they want to answer to one significant figure. So if I have to write this to one significant figure, I'm going to get -1. So that's my answer to one significant figure. Okay. Somebody said they bring going through alpha, beta, and gamma decay. Don't worry, all of this is gonna finish soon, right? I think you all have just one more week again, and that's it. right? Yeah, so somebody said make sure and hit like and subscribe. Yeah, right, make sure hit like and subscribe, right? A lot of people, they just here for they come to class, right? But I'm giving you this here for free, right? So, and plus feel free to share the link with others so you can get help, right? Don't never keep information to yourself. Always try to help as much people as you can. All right. Okay, so everybody getting the same gradient. Next thing they said they want the value of the y-intercept. Okay, now just for your knowledge, I'm just going to tell you something here. This particular experiment, you have plotted 1 over u against 1 over v. I'm just going to tell you from a theoretical perspective, what is actually happening here is that we are supposed to get a graph like this. The slope of the graph is supposed to be -1. And also this point of intersection on the y-axis and this point of intersection on the x-axis, those two numbers are supposed to be the same, right? So this intercept here, C, and this intercept here, C, they are the same. And if I want to work out the focal length, your intercept should be equal to 1 over f. Just letting you know that this is the theoretical or the theory behind this question. Okay, it is making use of the lens formula. Right, that's basically what we're doing here. So that's why the gradient is going to be -1. The next thing they want the value, right, on the 1 over u axis. Now, first of all, this is not the first time CXC has brought this question here. And in one of the questions, what they did, they asked you for the intercept on the x-axis and the y-axis. Now, based on theory, those two numbers are supposed to be the same. But if you do the experiment, they might be slightly off. If they are slightly off, then what CXC asked them to do in the question was to find the average. Add up the two numbers and divide by 2. In this particular case here, they just want the 1 over u axis. According to my graph here, that looks like 0.069. That's what it's looking like to me. Yeah, 0.069 around there. So 0.069, right, per cm. That's what I'm seeing here. Now, based on that, now we're going to calculate the focal length of the lens. Yep, that's the next part for 4 marks. Okay, so you want to calculate what is the focal length. So the formula that we have here is C is 1 over F. So therefore, F has to be 1 over C. So we're going to take 1 over our intercept, which is 0.069. And I'm getting a focal length of maybe about 14.5 cm. Right? So that's my focal length there, 14.5 cm. Right? Oh, we just have one more part to the question, a part E here. So some of y'all still think that CXC is bringing questions. They're using AI to bring questions. I honestly don't believe so, right? And the reason why I'm saying I don't believe so, some of you all felt that the maths paper was weird. Yes, the structure was a little strange, but some of those questions didn't make up the questions, right? I can guarantee you that. I'm telling you that. There's a question there that came on that paper. They did not make up that question at all, right? That's a question that is supposedly called measurement. They didn't make up that question. I can find exactly where that question came from. So we have 3 rays here that is heading towards a convex lens. And what we want to do, we want to complete what's happening here. So first of all, there are some rules when it comes to drawing rays. So let me give you the rules here one time. CXC likes to be different. These are the rules you need to know. So if I have a ray that is parallel to the principal axis, what happens is that the ray will do this. Okay? The ray will do that and it'll pass through the focal point. That's one rule for drawing ray diagrams. The second rule is this. If I have your principal axis here and you have a ray that is passing through the center of the lens, if it passes through the center of the lens, it passes through undeviated. Okay, so again, that is some rules regarding this. There is another rule as well. If you have a ray that is passing through your focal point, right? This is your focal point here, and the ray does this, right? If it passes through the focal point there, when it passes through the lens, it does this, right? So these are 3 rules here we need to know for lenses. So we're just going to apply that in this case here. So first of all, you have a ray traveling this way. So what's going to happen is that this ray is simply going to do this, right? It is going to continue along a straight line going this way, right? Then for the third ray, based on the rules that I gave you here, what's going to happen is that this is going to be here, right? This is what's going to happen on this side. And for this last one here now, we have a ray that is coming through here, right? And we need to figure out what is going to happen here. Now remember, this here, yeah, for this one here, all we're going to do for this third ray, since we have no rule for that, we're just going to make sure that the ray is going to reach some kind of focus here. Okay, so that's our diagram here that we're going to use for 3 marks. All right, so let's move on to question 2, right? This is May 2018, guys, right? This is May 2018. I have some more free marks in this paper here. Check this. All right, we have a table here. An atom consists of 3 types of particles. We have protons, neutrons, electrons, and we want to complete the charge, right, for each of these things here. So to begin with, CXC, they need to put the word relative here, right? They need to put the word relative charge. Because if I ask you for the charge of an electron, the charge of an electron is negative 1.6 by 10 to the minus 19 coulombs. That's the charge on an electron. So don't come in the exam and tell me to write charge. You need to tell me relative charge. Okay? So the relative charge is going to be negative 1. A neutron has no charge. A proton has a +1 charge. Okay? Easy, free marks here in the exam. Okay? Yeah. Yeah, I know a lot of people think so, eh? A lot of people think that I see the exam paper before. I don't, right? I don't, right? I know a lot of what I said was coming in the chemistry that came, right? That's only because I'm able to see trends, and I've seen practically every chemistry paper, every physics paper, every maths paper since CXE started those things. I've seen all, okay? If you put positive, negative, and neutral, you might get it correct. Yeah, you might get it correct, right? Let's see what else we have here. Right, we have an element here. Ooh, I can't read this. So it's radium, right? And it's 226, and it's 88. I think I'm seeing here, barely seeing it. So for each of them, identify the 3 particles present. So we saw a question like this just now. So first of all, the number of protons is simply the atomic number. So it's 88. The number of neutrons will be the mass number, which is 226 minus 88. So in this case here, it'll be 226 minus 88. We're going to get 138. All right, so that's our number of neutrons. Number of electrons is simply going to be the atomic number as well. So this is going to be 88. Now, the only time the number of electrons will be different is if they had a charge here. So some of you all doing chemistry, if there was a charge there, the number of electrons will be different. Okay, so that is part 2. All right, so in this next part here, they said, state 1 similarity and 1 difference between isotopes. So first of all, isotopes of an element have the same number of protons and different number of neutrons. That's the definition for an isotope. So in the physics exam, they can ask you what is meant by an isotope, right? Those are atoms of the same element having the same number of protons but different number of neutrons. So in terms of similarity, you're going to say same number of protons right? So that's similarity. When it comes to different, we're going to say different number of neutrons. Right? So that's what we're going to see here, different number of neutrons. So easy 2 marks again. We have in part B here. Right, so part B, they want to know what is half-life. I'm not going to write this again, right? Half-life is the average time taken for the activity to decrease by half its initial value. We saw this question just now. All right, this next part here, we have thorium has a half-life of 24 days. So I like to write things down. So T a half is 24 days, right? 24 days. So it undergoes beta decay, and we want to calculate the time it would take 10 grams. So we're starting off with 10 grams of thorium, and we want to go to 1.25. So first of all, we start with 10 grams. So after one half-life, because remember this thing is decay. So after one half-life, we expect to have 5 grams. We divide by 2. After a second half-life, you're going to divide by 2 again. So you're going to get 2.5 grams. And then after a third half-life, let's see a half again, you're going to have half of 2.5, which is 1.25 grams. Okay? So the question is asking me calculate the time it would take, right, for 10 grams to decay to 1.25. So you're starting off here, and we're trying to figure out how long does it take for us to reach here. That's what we want. Okay? Now, if you look at that carefully, that overall time there is simply going to be 3 half-lives. Based on the diagram, that's actually 3 half-lives. So it's going to be 3 multiplied by 1 half-life, which is 24 days, right? So that's 4 3s are 12, 2 3 are 6 and 1 7. So your time taken to do this will be 72 days. Right? Now they asked that twice. They just asked it in 2 different exams here. The one I did before was May 2019. Okay. What do you have here now? So this is the third question. What do we have here? So in this case here, define the term electric field. So again, we don't want to lose marks for definitions. So electric field is a region around a charged body right, where an electric force is experienced. Right? So make sure easy 3 marks here. Now they said draw the electric field between parallel plates. So first of all, there are a few diagrams we need to know for the exam. So first of all, between parallel plates, we expect to have an electric field that looks like this. It is essentially parallel lines with equal spacing. So when you're all doing this here, make sure, right? And you normally get 2 marks for this, 1 mark for the lines, and you have to indicate the direction of the electric field. Electric field always goes from positive to negative. They could also ask you for an isolated positive charge, in which case, this is what you're going to draw for them. Right, this is what the field looks like for an isolated positive charge. And again, your field lines move away from. So you're going to draw this. Right, if they had asked us for a negative charge, an isolated negative charge, then the field looks the same. But what happens here is that the direction is different. Right, the direction is different. So in this case, the field moves towards. Right, so that's for an isolated negative charge. They can also ask us for the field between two, let's say a positive and a negative charge. If you have to do that, then the field is going to look like this. Right? This is what the field looks like between two unlike charges, right? So again, make sure direction is important. You have to move away. Right? So this is what the field line looks like between a positive and a negative charge. Also, you can have two similar charges as well. All of these are questions they can give you in the exam. So for this one here, right? And for this one here, you're going to move away. Okay, so these are the 5 diagrams you have to know for the exam. Anyway, any one of them could go. Right? Okay, good. Right, what else we have to do here now? They said goes from negative to positive. No, that's not true. It goes from positive to negative. Right? The direction of a field, when it comes to a field, it goes from positive to negative. Right? What else we have here? We have something about lightning. So they said a lightning strike is an example of an electrostatic hazard. State one other hazard of static electricity. Right? So a lightning strike, that's an example, right, of static electricity. So one other hazard, right? So you can get a spark, right, when refueling, right, an aircraft. That's a hazard, right? The second one here, state one useful application of static charge. So one example you all can give them here is a photocopying machine, right? A photocopying machine makes use of static charge, right? I'm sure you all have this in your schools, right? Okay. What we have here? Oh, nice easy question. Right, this next one here, we have this part D. Okay, so we have an alternating voltage from a generator. And using the graph, we want to determine what's the peak-to-peak voltage. I'm curious, what's the answer for this? What's the peak-to-peak voltage here? All right, who is Nick Blue Nova? Yeah, shout out your channel. I know what you do on your channel though. Yeah, kind of skimming the chat, right? Sometimes, depending on which live I'm doing. So if I'm doing maths, I have like a million chats, a million messages, so it's hard to read. So I kind of skim the chat ever so often. Don't worry. Okay. All right. Everybody saying 20. Some people saying I see a 10 inside here. So they ask you for, first of all, the peak to peak voltage. When they speak about peak to peak voltage here, this is a peak here, and this is a peak here. In physics, when it comes to an alternating current or an alternating voltage, peak to peak is actually from here to here. So what's happening here is that you have 10 from here to here. All right, that's your peak voltage there. But you also have 10 this way as well. So the answer for this one here will be 20 volts. That's your peak to peak voltage. What about the period? I want the period in seconds here. What's the answer for that one? right? I want the value for the period, right? I see you all give me a formula and thing. I want to know what's the actual period, right? For this particular thing here. There's something people get wrong. See, look, I see different answers coming through already. All right, let's see what you guys are saying. So we want a period, right? So first of all, I want you all to understand, because I see this mistake happen to students all the time. One period is made up of one crest. This is a crest. It is a trough. Right? So whenever you are trying to calculate or to determine period, you're looking for one crest, one trough. Once you know one crest, one trough, you're going to measure from here to here. Right? That there represents one period that we call T here. So if you look at the graph here, one period is actually this 8 here. So first of all, students are able to record 8, but what they fail to do, they fail to look to see what unit we have here. That's important, and that's a trick that they bring in the exam sometimes. So whenever you're calculating period, and that applies to alternating current or even applies to waves in general, look at the time there. It is milliseconds. So this is actually 8 milliseconds. So now, CXC is asking us for the answer in seconds. So the answer is not just 8. You're going to have to convert that to milliseconds. So to convert that to milliseconds, you can just write it as 8 by 10 to the minus 3 seconds. And I would stop there. That's what I would do. Or you can divide it and you can write this as 0.008 seconds. Okay? Any one of them will be acceptable in the exam. So for this one here, I will use standard form. So that's 8 by 10 to the minus 3 seconds. Okay? People get this wrong in the exam, so be careful. And the next part here now, I guess they want the frequency. Yeah, they want the frequency here and the 4 marks too. Right, so what's your frequency? Okay, so first of all, there's a formula for frequency. Frequency is 1 over period. So in this case here, it is going to be 1 over. Now that's why they want you to put the time in seconds here, because to work with the frequency formula, time has to be in seconds. So this is going to be 8 by 10 to the minus 3. So when I work this out, I'm going to get 1 divided by 8. So I'm going to get 125. So the reason why CXC is giving you 4 marks for this here, they want to make sure you give the correct unit for frequency. Frequency is measured in hertz, capital H, small z. Okay. Yeah. No problem, Nick. Something I was going to say. So I just curious, guys, right? I'm moving on to the next question in a sec. I just want you all to shout out whatever school you guys are from, right? Just let me know what school you guys are from now. Everybody trying to big up the channel, right? What I want to know is, I want to know what schools are you guys from, right? I'm curious. All right, I see in Manchester High School, Jamaica, Waterloo, Pinal, right? You can also say what country. Some of the schools in Trinidad, obviously. I know the schools in Trinidad, right? Iris and Stevens. Anybody from Holy Cross College? Nobody from Holy Cross? Anybody from Holy Cross College or St. Joseph Convent, St. Joseph? In Trinidad. St. Joseph Convent, St. Joseph, or Holy Cross? If you're wondering why I'm asking, right? I actually went to those schools. Somebody said YouTube High. Right? Yeah, so like I said, I went to Holy Cross College in Arima, All right. And I also went to St. Joseph's Convent, St. Joseph. Okay. All right. I seen SAGs. Oh, wait. Somebody say Holy Cross. Let me see. Okay, yeah. One person say, well, at least I saw one person with Holy Cross. Great. Right. So I have somebody from my alma mater there. All right. Good. Okay. So let's move on. Let me move on to the next question here. Question 4 is on thermal physics. Question 4 is on thermal physics. Right, so big up to all the schools who are here. You're representing your school, right? Good luck in that exam tomorrow. It'll be good, man. It'll be good. Okay, number 4, we want to define each of the following terms. So we met some of them before. So I don't like to write out definitions. I might just type it out here for you. All right, so specific heat capacity. All right, specific heat capacity is the energy required, right, to raise the temperature of 1 kg of a substance, right, by 1 degree. Okay, so specific heat capacity is the energy required to raise the temperature 1 kilogram of a substance by 1 degree, right? That's specific heat capacity, and that is usually a small c. That's what it is. Okay, small c is what we use here. For the second one, we want heat capacity. So this time we don't have specific, we just have heat capacity. So heat capacity, right? That's not specific heat capacity. Yeah. So heat capacity is the energy required to raise the temperature, right? Or this one here has no kilogram in it, right? Of a substance by 1 degree. We saw this one before. So again, it's a big C that we use to represent heat capacity. And the relationship between both of them is big C is M by small c, right? That's something we need to be aware of. Okay, I've seen questions where CXC asks us that. Or like in part 2, right? Like in part 2. That's what they ask us in part 2. So in part 2, they want you to write the formula, right? Showing the relationship between big C and small c. So big C is small m multiplied by c. That's it. Right? Now I just grabbed this paper here, right? But for those of you who attended my my crash course in physics, right? You will notice that some of the same questions happen to be here, right? Just by accident, right? Just by accident. I didn't really select these just so. So it may look familiar to you all because this is part of my crash course material, okay? Let's see, what are they asking here? Okay, so this experiment here, they are using this apparatus in order to determine the specific heat capacity of a metal. Now, this same experiment here can be used to find the specific heat capacity of a liquid. This calculation here that CXC wants us to do here is for 9 marks. Okay, it's a 9-mark calculation. It's a very easy calculation once you know what you're doing. So first of all, if you want to find the specific heat capacity of a block of metal using an electrical method, then all we do, we drill 2 holes into the block of metal. One hole is, well, actually, you're going to put oil in both of them. In one of the holes, we're going to put a thermometer. In the second one, we're going to put an electric heater. And you all need to know this circuit diagram here. See this diagram here? You all need to know the circuit diagram here that we use in order to determine the power of this electric heater. You need to know that. Okay? Now, in this question here, they said the switch is closed for an interval for 900 seconds. You know the mass of the block of metal. It is 5 kg. They gave us the change in temperature. So they didn't give us T1 and T2. They just gave us the change. They gave us the current and the voltmeter reading. And we're going to use that to calculate the power. So we want to calculate the specific heat capacity of this metal. And it's 9 marks. That's plenty marks. So if you don't know what you're doing, you're gonna lose that, right? So you gotta be careful, right? Right. One second, I just watching the chat here. Yeah, okay. So I'm not taking on anybody in the chat that just there making a sort of noise, right? A lot of people here to learn, right? So I'm not really taking on anybody else. So first of all, let's work out. So how you do a question like this here? We can work out the energy, right, supplied by the heater. So it's an electric heater, right? So if it's an electric heater, to work out the energy supplied, so first of all, power is energy over time, right? So if I want to work out the energy supplied, I need to say power multiplied by time. So energy supplied by the heater is power by time, but they did not give us the power output of the heater, but they gave us current and they give us voltage. So we're going to use our next formula here to calculate power, which is I by V. So in this case here, you're going to use I by V multiplied by T. That's a calculated power that is, sorry, the energy that is supplied by the heater. So the current, we get that as 8.5. So this here is 8.5 multiplied by V, which is 12 volts, multiplied by the time. Now the time is how long we kept the circuit on for. So this is 900 seconds, so it's going to be 900 here. So in this case here, this is going to be 8.5 multiplied by 12 multiplied by 900, and we're going to get 91,800, right? So this is joules. That's the energy supplied by the heater, okay? So now we're going to make an assumption here, and the assumption is this. Let's shift some of these formulas here. Right, so the assumption is this, right? So this here is the energy that is supplied by the heater. The next thing we're going to calculate here is, or we're going to see, right? Assume all the energy supplied by the heater is absorbed, right, by the block, right? So that is our assumption, or you can tell them no heat losses, right? So if that is true, then we're going to use this formula E is equal to MC delta theta in order to work out what C is. So we're going to say M by C by delta theta is equal to the energy that was supplied by the heater. So the mass of the block, they gave us that in the question, that is 5 kg. So it's going to be 5 multiplied by C. I don't know what C is. Multiplied by the temperature change. The temperature change in this case is 50 degrees Celsius. So this is 50. And that's equal to the energy supplied by the heater, which is 91,800. So therefore, C is going to be equal to 91,800 all over 5 by 50. So therefore, C is equal to, right, 367.2. Right, now what you're getting marks for here as well is the correct unit. So this is actually measured in joule per kilogram, right, per Kelvin. Okay, so that is our specific heat capacity of this metal block here. Okay. Right. You're okay with this calculation? I hope so. So all we're doing here, we know the energy supplied by the heater. We calculated that first. Once you get that energy is being absorbed, right? That energy is being absorbed by the block here, right? So 1 second, guys. So just give me from the chat here right now. Can anybody identify themselves as students from my class? I have to be able to recognize that you are students from my class. I'll make you a moderator quickly, and you can bump anybody off that you want. Right? Anybody who's saying anything inappropriately, right? Just get rid of that. Yes, you can use that VIT is equal to MC delta theta. Yeah. Right. Somebody talking about lens question. We did one earlier. Right. Kelsey, I could recognize you here, and Chelsea. Right. So hold on. I'll make you all moderators. Don't move too fast. Right. All right, so yeah, I was trying to figure out, Karishma, if that was you, right? So Chelsea, I added you, Kelsey. Right, so I'll give you all the power here. If you all, anybody that you all feel saying nonsense, just kick them out, right? Right. All right, so I just put a few there, right? So some of you all I can't confirm for sure. I know you all say in your part of my class, right? But I can't confirm for sure, right? So I gotta be careful who I put in as a moderator. Okay. All right, so that is 9 marks, right? What else we have here? Okay, so number 5. How do you use that formula? I just use the formula P is equal to I by V, right? Right, so somebody's asking if we should have used joule per kilogram. So here's what's happening here, right? With respect to the unit for specific heat capacity, this is actually the SI unit, okay? But we also use joule per kilogram per degree Celsius. We use that as well, right? But the actual SI unit, when you think about it, what's the SI unit for temperature? If I would have asked you that, what's the SI unit for temperature? Everybody inside here will tell me it is Kelvin, right? That's the SI unit for temperature. So if I want the SI unit for specific heat capacity, then you should tell me joule per kilogram per Kelvin, not degree Celsius. Okay? We use degree Celsius, right, inside our unit there, but that's not the SI unit. Okay? All right. Number 5. Let's see what number 5 is about. All right, so number 5, we want Hooke's law, right? Oh, by the way, Hooke's law can come as question 1 in your exam. Hooke's law can come as question 1. So Hooke's law basically says that the extension, right, is proportional to the applied force. So the extension is proportional to the applied force, right, provided, right, that the elastic limit is not exceeded, right? I know some students in my class here, and I would have told them, I don't like to put this, but this is what CXE wants, so we'll put it. It's really called limit of proportionality, not necessarily elastic limit, okay? So this could work here for Hooke's law, and if you have a mathematical statement for Hooke's law, it is F is equal to K by E, okay? Where K is called our spring constant, okay? All right, let's see. So, okay, next easy 3 marks here. They want me to with the aid of a label diagram, explain what is meant by elastic limit. So first of all, if we plot a graph of, right, F against E, what is going to happen is that we get a graph that looks like this, right? But it starts a curve here. So first of all, between O and let's say A, right? This region there, that straight line region is here, right? OB is Hooke's law. Right, so the straight line region there obeys Hooke's law, and what's happening here is that this equation holds true in that region here. But once I go beyond the point E, what's going to happen here is that your graph becomes nonlinear. Right, nonlinear here. It's no longer a straight line, so it's not obeying Hooke's law anymore. So beyond this point A here, so this point A here is your elastic limit. Now, what happens sometimes is that when you go beyond the elastic limit and you remove the force, you get permanent deformation. So, you know, if you take a spring and you stretch it too much and you release the force, the spring could be permanently deformed. Okay? I saw somebody made an important point there in the chat. 1 degree Kelvin. Now, the thing is, it's a change of 1 degree Kelvin is equal to a change of 1 degree Celsius. Okay? So it's not just 1 degree Kelvin equal 1 degree Celsius. It's a change of 1 degree Celsius is equal to a change of 1 degree Kelvin. Okay? What do we have here? Okay, let's do this here because if this shows up as a data analysis question tomorrow, you have to be able to do this calculation here, right? On Hooke's law. Okay, so this one here, we have a steel spring, has a spring constant of 2 by 10 squared Newton per meter. Calculate the weight of an object which, when attached to the unloaded spring, produces an extension of 50 millimeters. Okay, so first of all, this is what we have. We have a spring, right? And right, so this is just spring here initially, but then, so this is the original length of your spring. So let's put something here to attach some weights here. So that's your original length. We normally call that L0. Then if you attach something to that that pan there, what's going to happen is that the spring is going to extend. Okay, so it's going to extend and we're going to end up like this, right? So that's me attaching a weight to this thing here, and it's going to stretch the spring. Now when it stretches the spring, this thing is going to get longer, right? Let's put it from here to here. So this is L. So your extension is simply going to be your new length minus L0. So these are little formulas we need to know. When it comes to the weight, one of the things that we have to do is use this formula. Weight is M multiplied by G. So when it comes to Hooke's law, these are the things that we're playing with here. And we also know that F is equal to K by E. Okay? Now let's read the question here. In this question here, they gave you the spring constant. So that means they gave us K. K is 2 by 10 squared Newton per meter. That is K. They said calculate the weight of an object attached to the unloading spring, right? If it produces an extension of 50 millimeters. So E is 50 mm. Okay, and we want to calculate the weight here. So first of all, we're going to use F is equal to K by E. So in this case here, we're going to say our K is 2 by 10 squared. That's your spring constant, multiplied by the extension. Now this is where the problem starts here. You see, this here is given in Newton per meter, but they gave you the extension in millimeters. And this is something you have to be careful with in the exam. I can't just plug 50 into my calculation here. I have to convert that 50 into meters. But remember, milli is 10 to the minus 3. So you can either take the 50 and divide by 1,000, or you just write it as 50 by 10 to the minus 3. So this is going to be 50 by 10 to the minus 3. And in this case here, it'll be 2 by 10 squared. Well, yeah, 2 by 10 squared by 50 by 10 to the minus 3. And we're going to get 10, right? Could you all double check that for me? Right? Anybody else getting 10? I'm just making sure. right? Okay, right. So people got the same thing. Great. Let's see what else we need to calculate here. Oh, they're giving you 5 marks for that though. That's plenty marks. Okay, the object attached to the spring fell from rest and it hit the ground 2 seconds after 2 seconds. Calculate the velocity of the object on hitting the ground. So first of all, remember you had an object here, right? It was attached to the spring and it fell. So it fell to the ground. So let's say there's a ground here. It fell to the ground and hit the ground here. What they want to know is what's the velocity when you hit the ground here. So first of all, when an object is free falling, it falls with a particular acceleration. Now, before the object fell, it had an initial velocity of 0. It wasn't moving, right? It was there just hanging. So the velocity was 0. The final velocity, we normally call it v, and we don't know what that is. That's what you're trying to figure out, right? Now, the time taken for the object to fall is 2 seconds. So t is equal to 2 seconds. Now, when an object falls, it falls with a particular acceleration. And that acceleration is equal to whatever g is, which is 10 meters per second squared. So we're going to use that information to work out what v is. So acceleration is given by v minus u all over t. If I rearrange this formula, I'll get v minus u is equal to a by t. So v is equal to u plus at. So in some schools, they would have taught you that velocity, final velocity is simply u plus at. So your initial velocity is 0 plus the acceleration is 10 multiplied by the time, which is 2. So 10 by 2 is 20. So your final velocity, or the velocity on hitting the ground, is 20 meters per second. Okay? Now this is something very basic. So all right. What else you have here? Okay, so question 6. So we just did a question here from the 2018 paper, and it was on transformers. Sorry, 2019. In 2018, they asked them about transformers again, yes? Check this. That's what we have here, right? So we saw another question where we had to label a transformer. So we have a transformer, and we want to label the parts A, B, and C. So first of all, A is going to be your primary coil, right? B is going to be your soft iron core, right? Where is C? What is C? C is the AC input, right? And what is D here? D is the secondary coil. So easy marks in the exam here. They want you to label your transform, right? Right. What else we want here now? They're asking about some formulas here. So they said identify the type of transformer shown in figure 6. What kind of transformer is this? Right? What kind of transformer is this here? Right? Everybody's saying step up. For those of you who don't know what kind of transformer here, you look at the number of turns in the coil. So if you notice on the right hand side here, you have much more turns in the coil here. So it's a step up transformer. So in this case here, we're just going to say step up, right? Transform, right? State the formula that relates voltage and number of turns. So basically the voltage in the primary divided by the voltage in the secondary is equal to the number of turns in the primary over the number of turns in the secondary. So 1 mark just to state that. for this next one here, we have a transformer, 5,000 turns on the secondary. Now, while you are reading transformer question, always write down what is given to you here. So the number of turns in the secondary is 5,000. 5,000 secondary. 50 turns in the primary. So number of turns in the primary is 50. The voltage supply on the primary is 12 volts. So VP is 12 volts. And the current of 6 flows in the primary. So that's IP, and that's 6 amps. Okay, so the first thing they want to calculate the input power to the transformer. So the power input to the transformer is simply the primary current multiplied by the primary voltage. So the primary current here is 6 amps multiplied by primary voltage, which is 12. 12 6 is 72. So that's 72 watts. Okay, 4 marks. Easy marks. Right? What else we have here? The voltage across the secondary coil. Right? Voltage across the secondary coil. So we want to calculate VS. Okay? So we can use the turns ratio to work this out here. So number of turns in primary over number of turns in secondary is equal to voltage in the primary over voltage in the secondary. Okay? Actually, wait, hold on. Huh? Yeah, we can use that. So we have primary, so it's 50 over 5,000 is equal to the voltage in the primary. I think it was 12. Yeah, 12 volts. So this is 12, and we want to work out VS. So remember, it's a step-up transformer, so we expect the voltage to be higher. So this is 50 by VS is equal to 12 by 5,000. So we cross-multiply, so we get 50 by VS is equal to 12 multiplied by 5,000. So therefore, VS is equal to 12 by 5,000 all over 50. So VS is equal to right? And I'm getting 1200 volts here, right? So that's your secondary voltage here. It's a step-up transformer, so we get 1200 volts, okay? You can use that too if you want. You can use, hold on. It doesn't matter what you use, you'll get the same answer here, right? Like I said previously, we have a turns ratio formula, and we also have a formula that involves power, okay? All right, when I'm finished with this paper here, if you all want me to do a specific problem, tell me the year and the question number. Don't tell me the whole paper. Huh? Like, so I saw a lot of people asking about a moment question. Find a moment question. You tell me one, right? Because it's hard for me to go and look for to find one now. You give me a question and I'll work it for you. Okay. The last part of the question, they want the right. We want the maximum secondary current here. So you want to work out IS. So again, we can use, so we know that the power input is equal to the power output. Okay. So the power output is IS by VS. That's the power output. And we know, remember the power input, we calculated that just now, right? I think we did. Yeah, 72 watts. So if you have 72 watts coming into the transformer, we expect, if it's 100% efficient, they told you that, the power output is also going to be 72 watts. So in this case here, we're going to put IS by VS as 72. So we want to work out the maximum current. Now the secondary voltage, we just got that as being 1200. So it's IS by 1200 is equal to 72. So therefore IS is equal to 72 all over 1200. So therefore the secondary current in this case here is going to be 0.06 amps. Okay, so that's a step up transformer. What? Somebody said they want the question to be a radioactivity graph. What do you mean for number one? Definitely not number one, right? If I were you, I would want a straight line graph, right? I will not want a question on radioactivity as my question, right? Because I have to draw a curve. I don't want to draw a curve in the exam. I want a straight line. Okay, let me see. Somebody said moments, right? 2017. When you say 2017, is it 2017 number one? Oh no, you're all talking about something else. Let me see something. 2017. Oh no, 2017 question one is on electromagnetic induction. How long you all think you should finish the exam? The exam is how long again? Make sure and stay. If I were you, I stay in until the end of the year. It's 2.5 hours, right? I will stay. If I'm doing an exam, I use in every single minute I have in that exam, right? You all ask about questions repeating. They definitely do in the paper too. They do repeat, right? CXC has reached a stage where paper 2 questions are repeated. All right, people say 2023 question 6. Yeah, somebody said the hardest the hardest moments question, right? So if I tell you all this here, my class knows this. So that question from June 1995, that's when I wrote CSEC, right? And yes, I love that question, right? That was a nice question they brought in the exam, right? 2021 question 2. I'm still trying to find your moment question, I'm seeing questions coming through here, but now somebody choose a hard question, right? So yes, I will do this question for you guys, right? I will do this question for you all here. So you all asking about moments. Let's try a moments question, right? Right, this was actually a difficult question, right? This was a difficult question. So I will do it for you. All right, so first of all, this is May 2021. Right, and this is question 2. Right, so you all ask about moments. This is a moments question here. So the first part says define each of the following terms. So moment of a force is the force, right, multiplied by the perpendicular right distance from the pivot. Right, this is what your definition is for the moment of a force. Okay, if I had a diagram here, I had a pivot here, and I had a force here, right, and this force here, right, and we have this distance here from the pivot, then your moment T is simply going to be equal to F multiplied by D. Right, that's the definition for the moment of a force, right? Force multiplied by the perpendicular distance from the pivot. What is meant by center of gravity? It is the point through which all the weight, right, of a body appears to act. Right, so those are 2 definitions here. We need to know that. Part B, what do you have in part B here? State 2 conditions right? State two conditions necessary for a body to be in equilibrium, right? So the two conditions are, one, the sum. So we could apply the principle of moments here. So the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. Right? So this here is what we call the principle of moments. CSEC can ask you to state the principle of moments, and this is what you're going to give them. All right? So that's one. The second one here, and some people, what they put for their answer, sometimes they say the sum of the upward forces is equal to the sum of the downward forces. That is acceptable, right? Or you can also say the resultant force right, acting on a body is zero. Right? So these are the two conditions for equilibrium. Okay. All right. Now let's see this difficult question that CSEC brought here for the students, right? Some of you all may get lost, so try your best to pay attention. So first of all, figure 2 below shows a diagram of a non-uniform wooden plank. So first of all, it is non-uniform. CSEC will use the words uniform or non-uniform. Uniform means that the center of gravity is at the middle of the plank, right? When you say uniform, it means that the center of gravity is at the middle of the plank. If it is non-uniform, it means that the center of gravity is not exactly at the center. So if I had a plank here, right, and if it's uniform, then your center of gravity or your weight here is going to act in the middle. If it is non-uniform, then what happens? Your weight is going to be off-center. Okay, it's not in the middle. So make sure you pay attention to these words here. It means something. So now they tell us that we have a wooden plank here and the length is 2 meters. So this whole thing from here to here, right, is 2 meters. So when they're telling you stuff, try to write it on one time in the question. Now, they tell us the weight of the plank, it is 1,000, and the plank is supported from a ceiling by 2 vertical springs P and Q, and the plank is attached at a distance of 0.5 meters from each end, and the center of gravity is shown in figure 2. Okay, cool. So, when the plank is horizontal, the tension in the spring P is what? Right? So, when the plank is horizontal, the tension in the spring P is 600. So what they're trying to tell us here is this. Now, when it comes to tension, tension is always directed towards a fixed point. So you have a force here acting upwards, and this force here is 600 newtons. That's what they're telling us. Okay? Now, at the same time, you're going to have a tension in this here, right? And that is also going to act upwards, and we don't know what it is, right? We don't know what it is. So the first thing they want you to calculate the tension in the spring. Now, first, if the plank is horizontal, it means that the total upward force, so you're just going to say total upward forces, right, is equal to total downward forces. Right? So the total upward force here will be the 600 plus the Q, and that is going to equal to the total downward forces. So that's 1,000. So therefore Q is simply going to be 1,000 minus 600. So therefore Q is equal to 400. Okay, so some students may not have realized that this first part here was pretty straightforward. Okay. Right? Would you all say any paper leak? I find that hard to believe. Right? At least I hope not. Right? I hope not. Every year, students just like to spread these things to scare people. Right? So just But I really hope it hasn't, right? I hope it hasn't, right? When my students spend all that time studying, I want to make sure that they get and they do well, right? I want to make sure they do well. Right? The only people who will be happy for this are the students who are not ready for the exam, right? And if something like that does happen, then what's going to happen, guys, here? They're going to scrutinize your SBAs. So if you did halfway SBAs, that's going to be a problem for you guys, right? Somebody say, how does the paper leak? It usually starts in some school, some teacher or somebody, they open something and they take a copy of the paper, they share it with one person. Once you share something with one person, that's it. Everybody has it now. Right? So yeah, let me just finish this question quickly here. I realize time flying. So next, so that's part one, right? That's part one. What else we have to do now? The next part. All right, next part is this. They said by taking moments about A, determine the horizontal distance from P to C. So they tell you where you're taking moments about. You're taking moments about this point here. And we want to work out what is the distance from P to C. Where is P? You want to work out this distance here, right? So let's call that X here. Because that's where you want to work out. So if we take in moments about the point A here, what you have to do, you have to look at all the forces acting on the plank and try to figure out whether it's a clockwise moment or an anti-clockwise moment. So first of all, this W here, right? Because this is your pivot here, E, it's going to rotate clockwise. This tension of 600 here is acting upwards, so it's going to rotate anti-clockwise. This Q is also upwards, so it's going to rotate anti-clockwise. Those are the three forces acting on a plank here. So if we take in moments about E, we're going to say sum of clockwise moments is equal to sum of anti-clockwise moments. Right? So first of all, clockwise moments, we just had 1. So that is going to be 1,000, this force here, by the distance from the pivot. Now the thing is, the distance from the pivot here is going to be 0.5 plus this 0.8. So that's going to be 1,000 multiplied by 0.5 plus x. Right? Make sure I'm saying that correct. Yeah, 0.5 plus x. We need to look at all the other forces here now. So first of all, in the case of P is an anti-clockwise moment. So that's 600 multiplied by 0.5. Right? So 600 and the distance from the pivot is 0.5. When it comes to Q now, what happened to Q here now? Now the full length of the plank is 2 meters. You have 0.5 here, you have 0.5 here. So what that tells you is that the distance between here and here, right? That distance here is going to be 1 meter. I hope you all seen that. That distance here is 1 meter. So that means that that is 1 meter. And we know from here to here is 0.5 meters. Right? So the distance of Q from the pivot is going to be 1.5 meters. So it's going to be that 400. Remember, Q is 400. We calculated that just now. So it's going to be 400 multiplied by 1.5. So this is 400 multiplied by 1.5. So in this case here, this is going to be 500 plus 1000x is equal to 600 by 0.5 is 300. And then plus 3/2. So that's going to be 600. Yeah. So you have a maths problem here now. So 1000x is equal to 300 plus 600 minus 500. So therefore 1000 x is equal to 639. So that's 900 minus 5. So that's 400. So therefore x is equal to 400 all over 1000. X is equal to 0.4. Right? So lots of people got this question wrong though, right? Somebody's asking how you know if it's clockwise. So first of all, you need to know where the center of rotation is, right? Or where you're taking moment about, and then visualize how the force is rotating. Remember, when it comes to a clock goes in a clockwise direction, and if the hands of the clock were to reverse, that's anti-clockwise. Okay? What is always a difficult topic for people? All right, so the topics that I've found students have difficulty with is thermal physics. Easiest topic out of all of them is usually radioactivity and waves, right? Most people find waves to be very easy. Right? People say they saw it. Stop riling up people. Stop riling up people. Right? Right? Predictions. Everybody want predictions, right? Now generally, I don't really give predictions when it comes to these things, right? There are certain things that I would prefer not come. I just want to run through one or two things quickly with you guys, right? One or two things quickly. One of the things that I notice students get trouble with is electromagnetic induction. So first of all, there are a few experiments that you all need to be familiar when it comes to electromagnetic induction. So for example, this is one of them. If I have if I have a north pole here and I have a south pole here, right? So I have two magnets here, right? North, south. And I have a conductor in the middle here, right? One of the things you have to be able to know is that when you have a conductor moving in a magnetic field, it is going to create, or an EMF is going to be generated. So what happens here, between the ends of the conductor, you're going to get a voltage. So one of the things we can do is to attach a sensitive galvanometer to this, and we can observe what is happening. Now this is an exam question here. CSEC can ask you, what happens if I were to move this wire up or down? What's going to happen? So if I move the wire up or down, what's going to happen is that you're going to get a deflection to the left and a deflection to the right. Okay? So up, down, you're going to get a deflection left, right. That's one question CSEC can ask you. CSEC can ask you, if I were to move up and down faster. If you move up and down faster, what's going to happen is that you're going to get a larger deflection. Because the faster you move in the magnetic field, the greater the voltage that you're going to create. Okay? So this is an exam question. Up or down, you're going to get a deflection left, right. If you move it faster up and down, you're going to get a greater deflection. Another question CSEC can ask pertaining to this is, when you move this horizontally, what happens? You see, with respect to the magnetic field between the magnets, the field looks like this. But if you have a conductor in it, and the conductor is moving in the same direction of the field, it means you're not cutting the field. So therefore, the needle on the galvanometer stays in the 0 position. Okay? Now, what CXC is going to ask you to do as well, they can ask you to predict the direction of the deflection. So first of all, if you have a current that is flowing this way, the galvanometer reading is going to look like this. It's going to move in that direction. If the current is flowing this way in your circuit, the galvanometer is going to deflect this way. Now let me ask a question here, because some students, they're not sure about this, right? What rule do we use to determine the direction of the deflection? Somebody says deflection. What is deflect? Deflection is the movement of the needle. You see, when you look at a galvanometer, there's a needle in the center, and it's going to either shift to the left or to the right. That's it. How physics have a formula sheet? I'm not sure why, right? Right, so based on the answers I'm seeing, I know there's an issue, right? I know there's an issue when it comes to this, right? Right, so some people saying right hand, some people saying left hand. So here's the thing, when it comes to electromagnetic induction, it is Fleming's right hand rule. Right, it's called Fleming's right hand rule. Right, that's what it's called, and this applies to electromagnetic induction. Okay, so for example, let's see, right, let's do back a diagram here. Right, let's say we have this here, and we have a conductor here, and this is the ends of the conductor, and let's say we connect it to a sensitive galvanometer, and we want to figure out what direction that deflection is going to be in. So let's say we push the conductor downwards with a force F here, and you want to predict the direction of the needle on the galvanometer. How are we going to do that? Students have difficulty working that out. So first of all, we're using Fleming's right hand rule. So let me ask a question. What do you all think? Will it move to the left or to the right? Right? Look at my diagram here, and I want you to predict for me the direction of the current. Right? Some people saying left. So here's how we're going to do this, right? So this is where students have trouble here. So first of all, I'm using my right hand. Now I'm not sure how it's going to look on your end when you see my right hand. This is my right hand here. So the first thing I normally do, I take my pointing finger or my index finger and I point it in the direction of the magnetic field. So that's a point north-south. So if I do north-south, Then your thumb has to point in the direction of the force, which in this case is downwards. So that's going to be like this. So what is actually going to happen in this scenario here is that your current I is going to flow this way, right? Now, if the current flows that way, it means that your galvanometer is going to be pointing towards this side, right? So some of you are saying, right? Right? So you're using your right hand, right? Fleming's right hand rule in order to do this, right? That's basically what's happening. Yeah, so you all, yeah, every year we get the same story, right? Every year we get the same story. People trying to say the exam leaked. I usually ignore those things unless I actually see CSEC says something. All right. They have some people out there just there to cause trouble. All right. All right. So again, using your right hand, your Fleming's right hand rule. So north south, you're moving downwards, so the current is gonna go there. If I were to reverse what's happening here, so that I'm gonna shift this here. Let me do this on. All right. Let's shift this here a little bit. Right? So this is what's going to happen here. We're going to get a galvanometer reading, but it's going to deflect to the right-hand side here. It's going to be pointing to the right-hand side. If we had a different scenario where we have this, right? So we have north, we have this, right? And what's happening here is that let's take a conductor again. And what CSEC could ask us is to predict the direction of the deflection. So in this case here, let's put our galvanometer here, right? So this here is our galvanometer, and CSEC can ask you to predict what's happening here if I were to move the conductor upwards, okay? So if I move that conductor upwards and I'm using my right hand, Fleming's right hand rule, you point north south, and basically what's happening here, you're moving upwards. So if I follow what's happening here, your second finger will point in the direction of the current. So the second finger is actually going to point this way. So the current is going to flow through the galvanometer this way. So therefore, you're going to get a deflection that is going to be pointing to the left. That's an exam question. This is something I see people get wrong in the exam. Okay? So we're using Fleming's right-hand rule to make that prediction. Now, this is one scenario for electromagnetic induction. Sometimes CSEC can ask you to describe an experiment to demonstrate electromagnetic induction. This is one. Another demonstration is this. If I were to have, right, now sometimes CSEC might show you a coil. Now when you want to draw a coil, what I suggest you all do is to draw something looking like a pipe like this. And when you want to draw your coil, you do this, right? I don't like the diagram CSEC typically gives us, so I like to draw it like this. So this here, think of this as a coil of wire being wrapped around a pipe, okay? And this here is also an exam question. They connect a galvanometer again, right? Across the ends of this coil here, okay? And they take a north pole, and they bring this north pole towards this thing here, right? And we have to predict the direction of the deflection. Now let me explain how this works. So first of all, if you take a north pole and you bring it close to a coil, what is technically supposed to happen is this. This end of the coil, right, is supposed to produce a north pole. Now why is that so? You see, if we bring a magnet close to a coil and the coil happens to be a south pole on the side here, it means that when you bring the magnet close to it, the magnet could go into the coil without any force being applied to it. And you're breaking the law of conservation of energy when you do that. So what actually happens here is that this has to become a north pole. So if I am pushing this north pole into that coil, what is supposed to happen is that the coil is supposed to push it back out. So here's how you're going to figure out the direction of the current. To do this one here, we're going to use what we call our right hand. So it's not Fleming, it's called the right hand grip rule, right? It's called the right-hand grip rule. That's what you're using here. So first of all, if you bring a north pole close to the coil, that end needs to become a north pole. Now, to figure out where or how this how the current is flowing, you're going to use your right hand. And what you're going to do, you see those fingers here, these fingers here, the 4 fingers, you are going to grab the coil, right? If I grab the coil, right, your thumb needs to point in the direction of the north pole. So if the north pole is to the right, and I grab the coil with my thumb pointing to the north pole, you'll notice where your 4 fingers are pointing. If you look at the diagram, the 4 fingers, in this case here, my 4 fingers are actually pointing upwards. So this here will give me the direction of the current that should flow in the coil. So if that flows this way, it means you're going to flow this way. You're going to flow this way. So therefore, my deflection is going to be to the left. Okay? Now, what is happening here is that when you bring the coil, when you bring the magnet, close to the coil, remember the magnet has a magnetic field. So when you take this magnet and you bring it close to the coil, you have the coil, which is a conductor, cutting the magnetic field. So therefore, an EMF is going to be induced in the coil. This is electromagnetic induction. Now listen to what I'm saying, right? Listen to what I'm saying. What is electromagnetic induction? Basically, what happens is that when a conductor cuts a magnetic field, an EMF is induced in the conductor. That's what it's saying. Okay? That is Faraday's law, basically, right? Once a conductor cuts a magnetic field, an EMF is going to be induced in the conductor. What is EMF? EMF is just a voltage. So you can do this in 2 ways. Either you have the conductor moving in a magnetic field, which is the first example I gave you, or you can have the conductor stationary, which is a coil, and you can move the magnet instead. So you're moving the magnetic field instead. Okay? So that's one scenario. You have to be able to predict the direction there. We have a second one here now. What if we have something like this? We have the same coil again, but this time, right? So let's draw. Right, so this is our coil here. Let's connect our coil to a galvanometer. Right, and let's say CXC would ask us to predict what is going to happen or where is our deflection when the magnet, so we still have the north-south here, and the north-south is moving away from the coil, and we have to predict what's going to happen. So if we want to predict what's going to happen, the first thing is that the north pole is moving away. Now, if you don't want to violate the law of conservation of energy, right, then what needs to happen is that this end has to become a south pole. You need to hold back the magnet while you're trying to move it away. Okay? You don't want it to be a north pole because the magnet will just be pushed out of the coil. So if this has to become a south pole, it means on this side here, that end of your coil is going to become a north pole. Okay? So all we're going to do, we're going to use our right hand again, and we're going to point our thumb in the direction of the north pole, and we're going to grab the coil. When you grab the coil, what you're going to notice is that your fingers are going to be pointing this way now. So if the fingers point this way, current is going to flow like that. So therefore, your deflection is going to be to the right-hand side. This is going to be your deflection. Okay? Again, that's an exam question. No. Hear what? Some of you all say you thought you're going to pass, right? The problem is I'm just showing you these are the difficult questions that come in the exam that the average student may not know, right? How good do you need to be the exam? So it depends on what you guys looking for, all right? I mean, if you just want to pass physics and you just want to get, when I say pass, I mean like with a 3 or something, you just need a half marker and do well in the multiple choice. But that's not what my students aiming for. All my students aiming to get grade 1. So that's what they want, right? So they're not aiming to get 50. They're aiming to get more than that, right? So here what you need to do, right? For this question here, try to go over the video, right? But this, you all need to know this, right? You need to know this. What else do we have here? So this is, right. There's another experiment that CXC can bring as well. And that's this one here that applies electromagnetic induction as well. What they could do, they can give you like a circular ring like this. And what they could do, they can attach, right? They can put some coil here, right? And they have, let's say, a DC power supply here, right? And let's put a switch here, right? And then on this side here, right? On this side here, let's say we put a galvanometer again. Right? Don't worry, we're not gonna predict what direction gonna happen here. We just need to see what happens when it comes to a scenario like this. So you have two coils and they attach to this. So this here is an iron ring. Right? So you have two coils attached to this iron ring here. We have a DC power supply and we have a switch here, S1. Right? Now, like I told you all, I think I've seen every single physics paper since physics started. Right? So for this one here, let me tell you what CSEC can ask you. They can ask you to say what happens when S1 is closed. Right? They can ask you what happens when S1 stays closed. Right? And then what happens when S1 is open again. Right? This is what CSEC can come and ask us. So first of all, when it's a DC supply. You notice it's a DC supply. It's not a transformer that where we have AC coming in. It's a DC supply. So when you turn on the switch here, what's going to happen? When you turn on the switch here, the current in that primary circuit there, right, it increases gradually. So therefore, it's creating a change in magnetic field. Once you turn on that switch here, and this is the answers you're going to tell them. You're going to get a deflection, right? So you get a deflection. Now, we don't know what direction here, and we're not going to predict that at all. They're not going to ask you that. Right? So deflection in one direction. Right? So we get deflection in one direction. When the stays closed, what happens here is that when you close the switch and it stays closed, the current flowing in the circuit is a steady current. If you have a steady current flowing in the circuit, then what happens is that you have no change in magnetic field. So therefore, the deflection is zero. It stays at zero. Right? So deflection is zero. And then when we open the switch now, so we close the switch and leave it closed. So the deflection went to zero. You got an initial deflection and then it went to zero. When you open the switch, what's going to happen is that you're going to get a deflection. Right? In the opposite direction. Right? That's what's going to happen. Get a deflection in the opposite direction. Okay? Right? For those of you who... I won't give you this. I won't confuse you, right? I won't confuse you. I can explain why we get a deflection and why we get a deflection in the opposite direction. Okay? Okay, so these are some experiments you all need to know. You need to know... Let me just explain something here as well. You all need to be able to understand the operation of a DC motor, right? I've seen this come for 9 marks in the exam. If you all have to explain this here, we are using Fleming's, right? Left-hand rule. Right, so let me explain how the DC motor works here. So first of all, let's draw our magnets. And by the way, you all more than likely, if you are given a question like this, you could be asked to draw this, or I've seen questions where CSEC drew it first and we had to explain how it works. Okay, so this here is not. Let's go this way. Right, so first of all, this is a simple DC motor here. Basically, we need to draw a coil. Now, what I normally do, I draw one coil, right? But in a real DC motor, you have multiple. Right, so label your coil. So I normally tell students label A, B, C, and D. And then what we're going to do here, we are going to put what we call our split rings. So in a DC motor, you have something called a split ring commutator, right? You also have your carbon brushes. So you need to put in all of this here. And what we normally do as well, we'll put a switch. That's a turn on and off the motor. This is your DC. It's a DC motor, so we have a DC power supply. What else am I missing here? You can put a variable resistor if you want to adjust the speed of the motor. Right? So this here is a simple diagram showing a simple DC motor. Okay? Your syllabus says you have to be able to explain the DC motor. So I'm going to explain this. I'm not going to write it down. I'm going to explain it. This session has been recorded. You can go back to the recording and listen to it slowly. When you turn on the switch here, what's going to happen is that a current is going to flow through the coil. So once you turn on that switch here, the switch is closed. This is your positive terminal. This is your negative terminal. Current flows from positive to negative. So first of all, CSEC can ask you to label this. So we can say magnet. So this is our magnet here, right? We need to label. So, right, I don't want to clutter the diagram too much, right? I like to draw something that's looking kind of neat. So this is the carbon brushes, right? They could also access to label this here. This guy here is the split ring commutator. Right, split ring commutator. What else I have to do here? Label this as your coil. Right, so I just showing you things that you probably could put on your label here. Now we have to explain what's going to happen and how the DC motor works. Right, so first of all, they will ask you what rule you're using Fleming's left-hand rule, not the right-hand. Left-hand rule is used for the DC motor. So if I follow the path of the current is flowing from positive to negative. So the current is going to flow through the carbon brushes. It's going to flow here. It's going to flow here, and eventually going to flow here. Now, that current through AB, we have to predict whether the coil is going to move up or down. That's what we need to predict. So using Fleming's left-hand rule, so we're using this hand now. So again, you're going to point your index finger north-south. Current is flowing this way. Your thumb gives you the direction of the force. So therefore, this here is actually going to move downwards. So this arm of the coil, AB, is going to move downwards. Current flows this way, current is going to go this way. If I use Fleming's left-hand rule again, based on that here, this piece of wire, DC, is going to move upwards. So in your answer, you must mention this Fleming's left-hand rule. So AB, right, how is that going to move? It moves down, right, according to Fleming. And the arm CD is going to move up here, right? So if you have these two forces, right, they're acting in opposite directions, what is going to happen is that the entire coil is going to start to rotate in that direction. CSEC can ask you to predict the direction of the rotation. So this coil here is rotating anti-clockwise, and what's happening here, it's rotating about this axis here. So you can draw a dash line here to represent an axis. So it's rotating about that axis there. So what's going to happen, the coil is going to rotate, but when it reaches vertically, because of the split ring, right, it's not going to make contact with the circuit anymore. The inertia of the coil is going to continue or cause it to miss that gap there. And the purpose of the split ring commutator is to ensure that the coil rotates in one direction only, right? Right? Yeah, Elijah, I sleepy too, right? I'm gonna bust it down a little bit too, right? Started at 5 here, so we approaching 3.5 hours here now, right? This is not my style, right? I don't like last minute things here. My preparation for exams last 2 years, right? I'm only looking for my students to pass, not barely pass. So this is the DC motor. You have to know the diagram. You have to be able to explain the operation. What's the purpose of the split ring? Now, if here are some questions here I can ask you. How can we make the motor spin faster? How can you make the motor spin faster? One of the things you can do to make the motor spin faster is to increase the current flowing in the circuit. We can also increase the strength of the magnetic field, and we can increase the number of turns in the coil. So that's an exam question. How can we increase the speed of the motor? Increase the current in the circuit, increase the strength of the magnet, and also increase the number of turns in the coil. Here we have that. Now that's the DC motor. When it comes to the AC generator, so we have something called the AC generator, right? Now the AC generator, the diagram is basically the exact same diagram, but there's a slight difference here. So for the AC generator, you have a coil sitting in two magnets. So you have a north pole here. Right, so this is our south pole, and again, draw your coil. Right, now the only difference here between the AC generator and the DC motor is that instead of us using a split ring commutator, we use what we call a slip ring or slip rings. Okay, so we have two coils here, and this is what's happening here. So what is going to happen is that you're going to generate a voltage across this. But what's going to happen is that you have to turn the coil. In order for the AC generator to work, you have to turn the coil. So when you have to explain the operation of the AC generator, we use Fleming's right-hand rule. Right? That's what we use here. We use Fleming's right-hand rule. Okay? Yeah, so like I said, these are some things that we don't want to see come in the exam tomorrow, right? All right, guys. So what's the time here? 8:30. Right. So I feel like I'm going to pause there now. Right. So guys, I just want to tell everybody, good luck. Good luck in the exam tomorrow. Read your questions carefully. Yeah, read your questions carefully, right? Please remember to hit like and subscribe, guys. Look out for some more free sessions, maybe next week, right? But I just want to tell everybody good luck in the exam tomorrow. Let me know how it was, right? I'm sure it's going to be great for my students, right? I don't have any specific predictions, all right? But the way our exams came for biology and chemistry, right? Let's hope it comes exactly the same way for physics as well, right? So guys, good night everybody, right? I don't know who else is live right now, right? Cohen might be live. You can go across if he's live. I'm not sure if he's on right now, right? But you can go check, right? But I'll see you guys next week, right? Take care everybody.